full. Are we good? All right, they've closed the doors, so you guys are all locked in here now. Sorry. I'm Chad Furman. I'm a product manager on the Ansible side, but for the context for this conversation, probably more interesting to you is I was a customer for a very long time. I used Ansible. I installed Red Hat Linux for the first time in 1997, so I've been doing this a very, very long time. But yeah, I came from an oil and gas company, so I know entirely too much about how things work in an industrial setting. So I think this will be a fun conversation.
For those who don't know, the microphone doesn't, or does it actually project?
No, it doesn't go.
No, okay, they told us it wasn't projecting in here, but it's for the online stream. That's why we're taking turns on the microphone, even though you can't hear it. Okay, my name is Adam Miller. I am one of the software engineers in the Ansible organization, and lately I have been Chad's partner in all things Edge, and specifically Industrial Edge more recently.
Okay, agenda. We're going to talk about all the things and talk about challenges. Get into what we've actually been working on in the Ansible space. It's all very community driven, of course, because that's where we start from the open source side. And then get into really interesting things we've done with common industrial protocols and actual real world applications, because I think that's what really matters is how do people actually use this stuff. So edge computing is a huge, huge pain if anybody's ever thought about it. Like a lot of people have been in the data center for a very long time, but thinking about how do you scale and manage and have the interoperability and consistency of all of these different things and tie them together, and how do you make 1,000 devices work the same? Or how do you push an application to tens of thousands of devices and manage them and know what their IP addresses are and what they're supposed to do or what they think they're doing and the telemetry that all comes back from that? I know there are some people here that I've worked with for many years on this, and I don't think anybody's actually solved it yet, but we're getting there. So who here knows, I like to make this interactive, so what does industrial edge mean to you?
Factory automation.
What's that?
Factory automation.
Excellent. Anyone else?
Agriculture.
Yep, absolutely. Anyone else? Fun. All right, cool. Literally anything that makes things. So agriculture, factories, cars, electronics, anything that could have robots or machinery and all of these things that are, if you've been in the IT space for very long, we always think about VMs and containers, but when you work with an industrial company, a container is something they ship things in. It is not something that they use for applications. So it's a different conversation, and I have that conversation often, like, yeah, containers. They're like, yeah, we run on Windows and VMware, and we don't know what a container is, sorry. So it's fun. So what we've been working on, Adam and myself, is working with different companies on how do you bring some of the best practices of IT into the OT space. So OT being operational technology, and that's what a lot of them refer to it as. So things like SCADA systems that control robots, and SCADA systems that control roller coasters, because yes, they actually do the same things from the same companies, which is really interesting, because at first, whenever we started going down this, me coming from a manufacturing space, I was like, oh wait, yeah, you probably use the same motors to control a roller coaster that you use to control a robot in a car manufacturing plant. Kind of cool stuff, but they don't know anything about IT in this space. Like, to them, IT is the guy that they call when their stuff breaks, and it is a ticket, and it is a waiting period. And now that they're starting to kind of talk to the IT people, and instead of them being the enemy, they're now becoming friends and starting to think about things like, oh, so automation isn't just about factory plant automation. Automation is actually about IT things too, because if you say automation in the OT space, to them it is process control automation, not IT automation. I think I kind of talked about this a bit. So here are all the different things that you see a lot in this space. Anything from devices and servers to sensors that are detecting things in the air. That was one of the big ones where I came from. They're always looking at particulates that went in the air, because there are laws about what you put in the air when you're an oil and gas company, sometimes. But it actually gets all the way to like substations from electric. And of course, there are central servers that are there that generally are ran by IT, but sometimes they're actually run by the OT people. And to them, it's just the servers. Like, it's not something they really know much about. It's just something they have to run all of the other things that they need. So unfortunately, we couldn't bring this with us because it would have been really expensive. But at Summit, we had some really, really cool booths with different companies we had been working with. So we actually had the Schneider Electric Siemens water. So this is how they do wastewater management in a lot of places. We had it where you could change the valve knobs, where you would change the water displacement in the tanks, and then you could actually rip out a server and it would continue to work. And then you could plug the server back in and it would reprogram the server and continue to work. So it was kind of cool to actually show real world interactions in this space, because a lot of times we're like, hey, here's a computer and we put a VM and a container on it and it runs an app. But it's actually cool to see stuff actually doing things. Am I doing this whole deck?
Yeah, just tell me where to jump in. I don't care.
You can take this one.
All right. Do you have the clicker?
Yes.
My turn to talk. All right. So one of the things that we've been doing is market research and talking to different customers and potential customers and just finding out where their problem spaces are. And we've identified a handful of business challenges. So this being kind of a summary of the business challenges that we're seeing out there from a plant manager kind of dealing in this actual space. This is their day-to-day. So the IT-OT convergence is still happening, and this is kind of almost like a culture shift that we're seeing in a lot of the industrial manufacturing, industrial edge, transit, logistics, these kinds of markets, where it's an adaptation of technology that has existed in the IT space for a while that we have to modify and evolve and develop new capabilities for to be able to address the OT space. Largely because the devices there are different, the protocols are different, the types of networks they talk on aren't IP based. There's a lot of legacy technology there that we have to interface with. You find different challenges for things like data gathering when your networking is either intermittent, bad, high latency, or low throughput. You find yourself having to design or architect the way that you deal with what you would traditionally do in a data center to adapt to these environments. So the Purdue model, which if anybody in manufacturing at all would be very intimately aware of this, effectively this is what all of the industrial, I don't know if this is like a requirement thing or just everybody does this, but the industrial manufacturing follows this model, and this is a security model for networking, and every zone may only talk to the zones it borders. Nothing can traverse from, like, so plant level near edge to operation level, nothing can actually go more than one hop. And this becomes problematic.
You can only go from the bottom up.
Oh, okay, yeah, sorry. And you can only go from the bottom up, so you can't reach back. So this becomes problematic because you have to deal with your ingress versus egress, and you have to figure out how to traverse these things to accomplish automation in a way that you might not have been able to otherwise, or in a way that you would have been able to otherwise. It just kind of depends. So this is a space that, from an, I guess, a traditional IT perspective, is very, very different, or the variables in play are different, more limiting. So we've had to find different methods to accomplish this.
I could rant about the Purdue model for like 2 hours if anybody wants to rant.
Yeah. So this is kind of a marketing slide because Edge is hot right now as a topic. Gartner loves to talk about it. Forrester loves to talk about it. This is new, like it makes its way around. It's not new though. We've had retail stores for as long as any of us have been alive. Those of them that have compute resources there, they were doing edge computing. This is just kind of something that has become, I guess, more relevant in our space specifically from a technology perspective, from a software perspective, from an open source perspective, because we are bridging the IT to the OT, and IT is typically where open source software and the things that we develop are able to be addressing those problem spaces. Now we're extending it into other problem spaces. And yeah, you do this.
Yeah, you do this. So, who all here uses Ansible or knows what Ansible is? Hands? Okay, some people don't know what Ansible is. And I asked that question so I could tell you what it is if you don't know what it is. So Ansible, actually, no, I'll give you that slide because that's the next one. Okay. So we built a platform around automation, and what we've had to do with this, so actually, I'll let you do your slide, and then I'll go back to that slide. Yeah, we did it backwards. Bad alignment on slides.
All right. Ansible is an automation tool. It is also an automation language. The idea of it is for it to be simple, composable, human readable, and if at all possible, idempotent. Idempotency allows you to only make state change when state change is required, such that you can repeat and rerun that automation over and over and over again and only inflict change upon any system or systems when required. The idea from the perspective of what we're building and what we have built in the open as an open source project is for it to be the automation language or the lingua franca of automation. The goal is for it to be universal. You should be able to learn this skill and then take it into network automation, security operations automation, industrial OT automation, IT automation, etc. We are doing everything we can to adapt the technology underneath and design it in such a way that it is pluggable, composable, and reusable, such that this automation skill set and tools and technology is adaptable and can be used throughout.
Let's go back one. Now I talk about the other one.
Well, I haven't gotten there. So one of the things that we did here, in light of bringing the automation technology of Ansible into the industrial edge, is we implemented a connection plugin for Ansible to be able to talk to programmable logic controllers over the common industrial protocol. So these devices are not connected to an IP network. They're not devices you can traditionally reach out and get to. However, they are connected to a backplane. That backplane does interface with a device that has an IP address and does speak IP. So we wrote software that has the ability to reach out to that controller. That controller then translates it to the backplane, and then we can traverse those SIP networks and automate programmable logic controllers. And for those who are not familiar, a programmable logic controller, or a PLC, is the thing that controls the robot arms, or controls conveyor belts, or controls different elements of the actual factory floor. The thing that produces widgets and boxes and vehicle parts and the bits inside of our laptops and our cell phones. So that can be interfaced using the same language that you can use to automate your Linux system via the Ansible automation language. So now I'll let Chad rant poetically about the automation platform.
So I'll add the PLC thing there. So where I came from, the way a PLC was managed before, and think about how many motors it takes to manage a conveyor belt. The only way to go and program them was someone walked around a manufacturing site with a serial cable and plugged them into each device and verify that they were configured correctly. Now you can just use Ansible to do that, which is kind of fantastic. So really short, sweet, we've created a platform around Ansible. So Ansible is a command line language. There's also a platform where we've built it and made a lot of the things. So as much as I love doing things on the command line, if I'm going to have to do it against 10,000 devices, I don't want to do that on the command line. It just is not a good way to do things. So we've created a platform to do all the things that you hate doing, like credential management, integrations, all of the self-service things, and you just go push the rocket to go run against those 10,000 devices. Oh, most important part about this, though, is the execution plane at the bottom. So remember that Purdue model? You use the execution plane with a network mesh to be able to get into those different parts of the environment. So now you don't have to worry about 5,000 firewall rules to get to every device, one firewall rule, one execution node, and then that can go against all the things in that particular network segment.
Aha!
Oh,
Gimme.
Pictures.
Okay, so the one thing that I want to touch on that Chad just said was about the automation mesh. So automation mesh has either a bidirectional or unidirectional communication method. So if you needed to function in an environment in an industrial space that does follow the Purdue model, you can set up to where certain zones only allow ingress traffic. So by doing that, that will put your automation mesh node in that space into effectively a pull versus a push. So everything from the automation platform still looks as though it's a pull, but everything will do store and forward intelligently based on the routing algorithm on down. And it's just Dijkstra's. Like, we don't have to be fancy about it. It's, this is a tried and true algorithm. It does what it does, and this allows us to deal with that space. So as Chad alluded to before, all configuration used to be done manually with these PLCs. We had to just kind of trust that it was fine because there was no validation. We couldn't really do CI on it. It was just a thing. So over here on the, let's see, right-hand side is it's a Pelican case, and inside this Pelican case is a Allen Bradley Rockwell PLC, a control node, an emergency stop button, a drive that actually will spin that little puck with the Allen Bradwell logo on it, and then that little blue thing down here. That is actually an LED, so it could be any kind of a status light. And we set up again, we couldn't travel with this because we just unfortunately couldn't. But the automation to accomplish that was all written with Ansible as Ansible playbook. So for those who don't know Ansible, the automation recipe, if you will, is called a playbook. All of this is automated from scratch. The second you plug it in, everything is completely programmed, and it will send that drive spinning. It will stop the drive. It'll spin up it'll light up the thing, the LED, and turn it off. And that was something that we did using this open source Ansible collection that we wrote called community.cip, CIP standing for Common Industrial Protocol. And we have the ability to read and write tags. So in a PLC language, it's effectively how you set or unset particular Boolean flags to inflict change upon a running system in a programmable logic controller. And then we can do audit and validation of information. So this allows us to do our audit trail and do testing. So this is effectively what an Ansible playbook will look like to command and control those things. And this is, it's just YAML. For those who don't know Ansible, it's just YAML. So everything that you have set up, you have a host, and after the host keyword is your host pattern. So the pattern will be the set of devices that you talk to, and there's a thing called an inventory. The inventory devices are individually itemized, either statically or dynamically by that pattern. We want to define whether or not we're going to privilege escalation. So become is to become a more privileged user. As part of the privilege escalation, we have a set of tasks. Each of them has a name. I have an indentation error. Please ignore that. We're going to call the namespaced module of ensure tags, and this is going to be the thing that takes care of the task operation. So we have a name of the tag and a value. And again, that is an idempotent operation. It will only make change when required. We want to gather fact data. We want to inspect the current state of the running system so that we can then validate it later if we would like. And then also we're going to verify our firmware version. And tag value for the sine wave. That was what that one was. So that is a sine wave generator, which was part of a demo that we had that would actually start to articulate a sine wave on a human machine interface. Okay. And that's kind of the goal, is for it to be human readable, easily composable. And this down here, this is a templated variable. This is part of some of the string interpolation magic of the Ansible automation language that there's plenty of wonderful documentation out there if anybody wants to check that out. Okay, so beyond that, we also have for doing device edge. So if you have compute nodes at these environments or in these cabinets that are co-hosted with your programmable logic controllers, Red Hat has a operating system that is based on a technology called RPM-OS tree. It is immutable, it is composable, it is easily distributable, it is a Delta application of an update, and it is atomic in operation. And we created some collections to be able to automate the lifecycle management of that entity. So OS build is how you actually build your operating systems. They are bespoke. They are artisanally crafted by you and your team. You will effectively pass in the blueprint or the desired outcome of your image. And then from there, we can do a full deployment, lifecycle management. We can, I'm sorry, I keep saying lifecycle management like that means anything. We'll set up an RPM-OS tree repository. We will actually automate the distributed update of systems. So to Chad's comment before about tens of thousands of hosts, we can do this at scale with tens of thousands of hosts. We can do the full rollout. We can do the update system. And because of the nature of OS tree, we can do it in these fractured environments with bad network, with low fault toleration, things like that. Because I like to pose this question for those who run RPM-based distros or any traditional package manager, DPKG, I don't know, package build, pick one. If you're updating your kernel and it's in the process of rebuilding your initRD and you kick the power out from underneath the server, will it boot? It's Schrodinger's server. We don't know. We don't know until we try. Whereas with this type of a system, that cannot happen because it's either all or nothing, and if there's a failed attempt at a boot, it will roll back to a previously known good state. And this automation that we've created allows you to do that. And then the next phase of that is microshift. So for those who are familiar with Kubernetes, who want to do Kubernetes at the edge, there is a minuscule version of OpenShift, which is a Kubernetes distribution called microshift. And then we have the ability to run application payloads out on those devices, build the images based on RPM-OS tree-based technology for those, do a full lifecycle management of that as well. Lot of stuff in one slide. I apologize. No. Yes. What?
So you can do Fedora and CentOS and RHEL with.
Oh yeah. With these, we can do Fedora, CentOS, and RHEL with these. So we can do a CentOS stream 8 and 9. Any current non-end-of-life Fedora, and Red Hat Enterprise Linux 8 and 9. Yes. And we full CI test all 3 of those for across each of their releases. So if something breaks, please let us know. We'll add a regression test and make sure we don't break it again. Yeah. Chad. Oh, no, wait. I already talked through this without diagrams up. I'm very sorry. Very quickly, this is basically the flow diagram of what these, we have 10 minutes.
This is the last slide.
We can do this. I believe in us. This is the flow diagram of what the automation content that we created does, and it allows you to have your image builder host, your RHEL for Edge image gets built there. From there, we have our device blueprint, which will define the curated content that you would like to put into it. That will generate it. We will extract the contents to then serve up for your update system. And then we can roll that out to your device edge images. And we also have a boot ISO that can be downloaded and you can flash devices with it, that kind of thing. We actually also have a tool set to be able to do credential injection post creation of the ISO. So that way you can, depending on what your chain of trust or your processes are, those kinds of things. And then for the microshift one, the only thing that you add there is you have day 2 operations of doing the application deployment and lifecycle management.
That's the microshift one added. Yeah, there you go.
Ooh, he added fancy words.
You did actually.
Did I? I haven't slept. I arrived in this beautiful town at midnight midnight last night. So bear with me. I lost my train of thought.
It's all good.
Chad, it's your turn.
No, we're done. No, that's a sales slide. We don't want that. Questions? Because I'd much rather listen to you guys talk than me and Adam talk.
We talked a lot.
How did you make your talk so polished?
Is he being serious?
No, God, no.
Okay.
Chad, Adam, Chad. Adam Williamson is a fantastic human and a grade A heckler.
Yeah. Well, no, I'm waiting for Peter. He hasn't heckled yet at all. No, nothing. Okay. That's good. No beer for you.
Hey.
You said it as something broken. We can let you know and you'll add a regression test for it, right?
Yes.
Yes.
Please build me an image in FIPS mode.
Oh. Please put
Peter,
it.
he needs FIPS mode.
Please put an issue in for that, and then I'll send it to Peter.
Yeah. So the
If you guys don't take about this today,
Excellent. Peter's working on this. It sounds like.
we've spoken about it in the past, yes.
yeah.
It's on the backlog somewhere.
Yep. At the end of the day, we just use the OS build bits behind the scenes.
Yeah, so the thing that we build is the automation, and the thing that we try to ensure is that it's easily consumable and repeatable. If you need core operating system technology added, we will gladly refer you to our friend and colleague, Peter, in the back there.
Toshio?
Yeah, so those sort of functionalities go to the relevant edge node, which then may go to the Ansible team, or it may go to the OS build team, or whatever sort of handles.
We have a bi-weekly, believe me. We talk. Okay, I'll repeat them. Yeah, sure.
Yeah.
Toshio?
Do you have a place to plug in CI of the image that is built?
Do we have a place to plug in the CI of the image that is built? That's a him question.
Yes. Yeah, I mean, so literally the build that comes out, the way that we do it is we just provide you an example playbook of how to do it, and you just put your inputs. At any point in that phased process, you can just pause, extract the artifact, and then send it to a pipeline. And you can actually do that in your Ansible playbook. So you can have the CI validation occur, and then allow the playbook to continue and perform your CD for you if you want, or you can then pipe that over to another system for that. If you want to use Argo or something else or whatever's hot this weekend.
All of our CI is in the GitHub, right?
Yeah, I mean, all of our CI is in the GitHub. I don't know if it's particularly like the best way to do CI. The way that we built CI is integrated into the open platform that the Ansible open source project uses. So it's all the data is there. Everything is open and available. The only thing that's not is our cloud keys, because we don't want people mining Bitcoin on our on our AWS bill. But yeah, it's all out there. We could definitely absolutely plug into any system there, and that's kind of the goal, is to offer an opinionated method of doing it, but be flexible when needed.
All right. Any more questions?
Maybe one question for the images. You using the Kickstart file, you have one image per Kickstart file, right? You cannot inject the
Repeat the question.
Kickstart file after the installer image is built.
So the question is do we have one Kickstart file per image, and are we generating the Kickstart file, or can you add one after?
If you need to rerun the pipeline, build an image, if you change the Kickstart file.
So
I don't know, like, don't think of it all.
okay, so if you want to change a config, do you need to rerun the whole pipeline if the config can be addressed in a Kickstart? You can do either. We will support either. So the options are there in the automation to add Kickstart changes, or post-build, you can just supply your own in the boot line like you otherwise would. Yes?
You've mentioned that one of the strengths of Ansible is that it only applies and do changes when it needs to. How is that automation? Does it not recreate the OS build, image builder image if you run the automation?
So the way we do that is with versions. So versions are either provided or auto incremented, and you have to actually tell our automation that you want it to auto increment and create you a build every time you run. Otherwise, it will come back and say that that version has been built and is already cataloged and indexed. And my laptop's going to sleep. No.
Oh my gosh. Escape.
You know what? It's fine. It's fine. Yes.
How do they solve security in the real world? Because it sounds like with Ansible now, like a single person can control thousands of devices in a factory, and that can go wrong, maybe, or either.
Do you want to? Okay.
Role-based access control is your friend. So this was that conversation I had around doing things on the CLI for 10,000 devices is not very good. So within the platform, there's definitely role-based access control, and you would assign different roles to different groups. And coming from a company that was really 12 different companies, that is a very tedious job, but it's very important that you think about who has the access to what roles and the separation of duties of who can do what. So definitely you would need the platform and do that within the platform. Architecting identity is a whole different thing that nobody ever thinks about until they're like, oh wait, we shouldn't let Steve do all the same things that Adam does.
There's also a centralized logging and audit within the automation platform. So the automation platform is composed of basically 14 or 15 different open source technologies integrated together, and one of the things that are in there is the SSO, the role-based access control, policy management, that kind of stuff.
So we can still have one unhappy employee destroy the factory, but we'll find weaknesses of the
Yes.
If you granted one employee enough access in the role-based access control to destroy the factory, yes, you could find them.
It may be too late, but yes.
Right, so from my experience with some of the industry automation stuff, if the production line stops, that's going to cost you millions of dollars in a very short amount of time. So how do you ensure that the change that you're doing works? Do you just have a separate environment, run this there, and then hope that it will do the same thing on the production?
So the question was, how do we ensure or basically, do you have like a dev test type of an environment for this? Yes, you should absolutely have development environments. The question is how much is it going to cost to have a development robot environment in manufacturing? And I can tell you, because I've set them up, it's really expensive, but it's worth it if you can automate an entire factory floor that becomes hundreds of factory floors. So there is a cost to benefit there, but yeah, you don't want to test this. Do not test this in prod. I mean, I test my code, but I only test it in prod, except at a factory. All right, I think we have 1 minute if there's any other questions.
Out of time.
Out of time. Oh, wait.
Question.
Last.
Ansible is good for reading, but it can be challenging for writing. Are there any helpers to help me build the automation platform?
So we actually just announced an AI platform to do that. So we're working, it's in the upstream in a beta right now, but it's called Ansible Lightspeed. The question was, is there a way to write helpers?
There's also a thing called Ansible Dev Tools that I highly recommend you check out. It's integrated into VS Code and the language. We're out of time. The language server can also be used from other editors like Emacs and Vim if you're, we got to go.
Ricky, they told us. Yeah, definitely look at Lightspeed.
Also, our friends over at Steampunk wrote some cool stuff too. Check it out.
Awesome. Thank you, everybody.
Yeah, 1, 2, 1, 2, 1, 2, 3. Is it in orange or red?
It's
Red, orange.
in the end of the green zone.
It's in the green?
Yes.
Světla můžu přitlumit, potřeboval vidět. Světla můžu přitlumit, to asi. Jo.
Good afternoon, everyone. I'm Alessandro Rossi. I'm a former redactor for 2 years. I've been a redactor for 2 years now. And today, thank you so much for being here to this session, both live on stream and where we watch the recording. I'm so excited to be here, and I would really love to thank you, all of you, for the trust that you gave me today, because we will see this in a moment why. Many of you may probably have seen my face here and there, both on LinkedIn or on GitHub or whatever. And I'm actually working as a senior specialist solution architect in Red Hat. And basically, I've always worked in the open source community, both as a contributor on my project and of course also with cloud native technologies. I started to look at Kubernetes, OpenShift, and whatever is related. And one of the important things today is that, and this is the reason of the trust, is that it's the first time for me being here at DevConf and the first time ever presenting at a conference, so don't be so tough. Well, today's session will be mostly oriented towards Edge and how to automate at the Edge using event and event-driven automation with Ansible. So I just prepared a quick agenda to guide you through what will be the steps that we are going to take today. So the first thing, we are going to start with an introduction of the Edge. So what is Edge computing? You're probably very knowledgeable about this, but it's always good to have a quick refresher. And how we can automate some of the use case, the most common use case at the Edge, and what are the benefits of automating at the Edge. And then we are going to focus a bit more on events. So discussing a bit about events and what actually does it mean to automate with events. So what is the actual idea behind this kind of, this different kind of automation? And I prepared a very small demo that will be covering some of the use cases that we will touch on during the presentation. And of course, at the end of this session, there will be a Q&A, so feel free to also ask questions also during the session if you want. It's all fine, perfectly fine. So let's start from the beginning. So we heard a lot about edge computing, and it's a way different way of calling something that we were used to deal with also in the past. When we talked about IoT devices, disconnected environments, we were already talking about the edge, but now it's starting to get a very hot topic. Also because we have the chance to completely decentralize our computing, and our different use cases can be really self-consistent, self-feeding, and basically doesn't require too much resources and too much compute power, for instance, or connection, or everything that is related to a data center can be just split into very little pieces. And one of the biggest benefits of this is that we can really start decoupling all of our different workloads and having different sections of our workloads, application, calculation power, and everything in sites that were never covered before, or were difficultly covered because we had restricted protocols, we had different access to this kind of places, because maybe it's a disconnected site, or it's a very connected environment. And of course, one of the importance of the biggest thing when talking about edge and automating at the edge is the response time. Because sometimes we need faster reaction times in respect of other potential use cases, like doing normal automation, like patching a system, or having configuration of a web server, or configuring our infrastructure. We potentially need to react faster to anything that is happening at our site. And we don't have the control of that, because maybe we cannot access that at that point in time, it is completely disconnected, or we have some limitation of any kind. So why it's a good idea to start automating at the edge? Of course, one of the biggest use cases and one of the most common use cases at the edge is, of course, configuration management. We want to streamline the configuration of our devices, of our sensors, of our small computing units that we maybe have there for collecting data, or having some interactions with local components that cannot be automated from a data center, for instance. Or we just want to have a consistent configuration across multiple kind of devices. So maybe we can have also some sensors that require different, each sensor may require different configurations. So we need to be able to control everything from one single place. Security, because maybe in our sites we want to enforce some security policies, SCAP or PCI DSS, or anything that can make our devices and our environment compliant with our regulation, local regulation, or just government regulation, if we are talking about a government agency or a government entity. And of course, one of the use cases that will also be covered in the demo is monitoring. Why? Automating at the edge can be good for monitoring and remediation. Because actually, when we are going to take control of our devices, so having our configuration in place, being able to produce metrics based on any potential activity. So if it's a sensor, it can be the data from the sensor. If it's a computing unit, it can be how the, for instance, the model that we are trying to work on for that particular device, how it is performing. If we have any leak, potential leak or power outage or network outage that we need to take care of in a very fast way. And we can also implement this in a sort of self-healing fashion. Because actually, and we will see this later in the demo, we can also host the automation at the same site without even caring about that. Because it's there, it will be running, it will be checking for everything that is working, and we can especially configure and extend this kind of automation. And another use case is the idea of having rapid developments. Whether it is a containerized application, whether it is a package that needs to be released, whether it is a firmware upgrade or a software upgrade that we need to deploy, we can do that at scale, and we will talk about scaling in a second. We can do that at scale and potentially with very limited downtime. Because actually, we can take care of that, integrate automation in our release pipeline. We can, for instance, take decisions based on how the deployment is going. So we can decide to extend the way of our deployment, of how our deployment is happening. And of course, scalability, because we are talking about, when we talk about edge device, we are not talking about a small bunch of nukes or a small bunch of sensors. We are talking about sometimes very big numbers. We have some customers also that are starting to get more into the edge computing and starting to, we are talking about 10,000, hundreds of thousands of nodes or sensors or devices. So we need to be able to scale in a very fast and streamlined way. And the last thing, of course, we already mentioned that, but we need real-time reaction times. Because we cannot afford having a component starting to fail, or we cannot afford having a deployment failing for one of the data collection units that we need. We need to put remediation in place. If a device is failing, we need to find a way to take that device, take it offline, or try to remediate what's happening, and then we can be able to, make use of it again. And of course, all these things are pulled together, but we potentially need something different to do, because the normal automation, the standard automation, may not be the best fit for this kind of use cases when we are talking at the edge. Because we are talking about, very definite use cases, and we don't have a dynamic adaptation of the automation. So we have some commands that we need to put, and we write our playbooks if we are talking about Ansible, because we will talk about Ansible. But we are going to just have a configuration in place. This configuration will be deployed, but what if we need something different? So what if we need to adapt our scenario to the automation to our scenario? And this is how events can start to get in the game. We all heard about events. Events are potentially everywhere. when we are talking about an S3 bucket, for instance, when you put a file in an S3 bucket, it can generate an event. You can create a message, put a message on a queue. This is potentially another event. When the sensor is starting to ingest data in our data center or in our devices or whatever, it is actually generating an event. It can be analyzed, can be processed, and we can do something based on the output of the analysis. And one of the other use cases that we always use with our customer is also the interaction with tickets. So if we are, if in our ITSM we are creating a ticket for deploying a node in the remote in the remote location that is not reachable from our data center for any reason, we can put in place some kind of automation based on events, trying to make this kind of automation reactive to what's happening. So when we are creating a request or a ticket or whatever, we can still process that and have the automation react to that message and also potentially close that message based on the automation, respond to that message, escalate that message. And another important aspect is coming back to monitoring, alerting. So if we have our platform, thinking of OpenShift, thinking of any other potential platform that we have in place in our environment, we can and need to react to what's happening in the platform. So if the platform emits an alert, we need to be able to identify what the alert is about, take a remediation on that, and apply it. So we need a bit of a switch of context, because actually we are used to traditional automation when we have some issue commands, we have a set of defined machines or potentially dynamic machines, but we have a potential issue, it's synchronous. When working with events and when working with dynamic data, we need to be able to react to each and single event that is happening in our platform. So it's not just about, okay, I need to configure this, I run my playbook, this is what's happening, I can also wait for the playbook to end because I had this task today, the playbook does this. When we are talking about events, it's quite different because maybe we have like 10, 100, thousands of events and alerts that are happening in our platform. And we need to be able to manage all of those asynchronously and, of course, just in time. So we need a faster reaction time, even in this case. And this is actually how it is changing. So it's not about just having a command issue, but this is something that is driven by the event. So it's the event driving the automation. So you have potentially different sources that are emitting different kind of events all day long, all night long, forever, and you need to be able to react each and every single time. So basically, if we think about events, we can define three big questions that we need to do. The first one is, we are interested in where is the event coming from? So what is the source of our event? Is it a Kafka queue? Is it a webhook? Is it an MQTT listener? Where does the event come from? Then we need to process it, because actually, okay, we received the event. We are good to go. It's probably a JSON message or whatever, XML formatted. We can do this in any way. But we need to do something with that. So we need to also define how we are going to treat our event and what is the outcome of this processing. Is the what. So what we need to do based on this one. So we need a source, we need something that processes the information, and then we have something that is actually actuating the automation based on the information that we gather. And this is why we are talking also about Ansible today. Because Ansible is one of the best fits for this kind of use cases when it comes to event-driven. First of all, because you don't need an agent. So we all know that the Ansible is agentless. The playbooks are very easy and human-readable content that we can reuse, implement, and distribute. And we have another advantage, that Ansible is community-driven and partner-driven. So also the community and the partners can contribute to the code base. And of course, covering different devices different protocols, different connection methods, and this is crucial, especially when we are talking about a very heterogeneous set of devices, like it can happen at the edge. And the most important thing is the last one. So we have dedicated bits for event-driven automation. So we have a collection that will be also implemented in the Ansible platform controller that will be actually responsible for managing the event-driven part. So it is implementing, and we will see this in a second, new resources that are called rulebooks, where we are going to define exactly what we said before. So we are going to define the where, the how, and of course the what will still be an action, a command, a playbook, or whatever. So let's see how this is translated. So we have the sources. So in the event-driven Ansible bits, we have the sources that can be, as I was mentioning, a Kafka topic. I recently created one for our demo. There is the MQTT connector. We have the community working on all the kind of connector. Also, Andrew Block created the one for Kubernetes for interacting with the Kubernetes cluster. And this is why I was talking about it's also easy to implement. It's not something that is rocket science, because actually I'm not a programmer, so I was able to create a Python script for the MQTT source from scratch based on what was already available. And this is quite crucial, because having this possibility of extending the use cases potentially in an infinite way, basically only our fantasy can be a limit, because as soon as we are able to create something to interact with our source of events, we are good to go. This is exactly what we need. And of course, we have some rules. So once we have identified the sources and got the event from that source, of course, we need to do something with that. We will see a very small snippet from the demo later, but it's basically a sort of event processing queue where you're going to put the condition based on the event, what is multiple condition, combination of conditions. We will be able to label our input, manipulate the event itself to make it understandable to our automation itself. So we will be able to further process our events even before using it in the automation. And of course, the last part are the actions. The actions are basically a command, a playbook that can be run, relabeling our input, saving the input from somewhere. And these all together, combined, is giving us a real way of managing events and managing automation with it. So just in a few seconds, I will be showing you a very small demo that I created. And basically, the use case, it's kind of funny because the next slide is a bit weird, but this is exactly the idea. And this happened to me last year. So we've always think about, industrial use cases, medical use cases, that are of course a big thing. But what about the little things, like a fridge in our house? So we all have a fridge. And the fridge, at least in Italy, when it starts getting hotter and hotter, you can feel that the fridge is not actually working at a very good condition. So, the groceries are not feeling so good. You're starting to have a mid-cold, mid-hot water and stuff like this. And this is even worse when you are out of your house and you cannot control this. So what is the idea? The idea was, okay, let's think about a potential use case where you have different sensors, one in the outside, one or more, of course, in the outside, a couple of sensors on the floor and on the roof of the room, and then one sensor in the fridge. Of course, the fridge should be, let me say, a sort of intelligent fridge, making it like just having an interaction with an external device, whether it's via wireless, whether it's via Bluetooth or whatever. So you just need something that is able to interact with that device. And what is the actual use case? The actual use case is why we cannot adapt the temperature of our fridge, the working temperature of our fridge, based on what's the temperature of the outside and the inside sensors. So what I was thinking was, okay, I cannot implement it for Unreal because I cannot bring something here. So I decided to create the version of this use case in a sort of containerized way. So I created a Quarkus application for all the sensors and the fridge itself. And then we will see this in a second. So the digital version is something like this. So we have, everything is based on Red Hat Device Edge. So we have a potential device running in our house that is hosting Red Hat Device Edge. Of course, coming back to the previous session, if you were here, we were talking about the image builder, how to create my microshift ISOs and stuff like this. This is exactly the same scenario. So I created my Red Hat Device Edge installation. I created the Quarkus application for all the sensors, and I have a small configuration here that is based on the Quarkus application. So the Quarkus application has a configuration that is our let me say, target of the automation, because we are going to change that configuration, redeploy the application, and see how this adapts to what's happening. I deployed a very small installation of Mosquito, it's a containerized Mosquito, and on the other side, we have two other components, one data aggregator and one actuator. The data aggregator just takes care of getting all the information from the sensor, aggregate it, and send it to InfluxDB. And the actuator, we will see the connection in a second, will be the actual generator of our event. So it will take care of monitoring the data here. So if something changes, it will send emit an event that will be then processed by Ansible, and Ansible will take care of adjusting the configuration. And the good thing is that the actuator, now it's just a very basic Quarkus application. As I told you, I'm not a developer, so it's nothing really complex. But the idea is that this actuator can be potentially anything. It can be an application running, implementing a model, an AI model, or a machine learning model to just react in a better way, or of course adapting to every single change. So the cool thing about this is that it's not just having a very simple use case, because it's not very simple. It's, as I told you, it's not rocket science. But these are really covers most of the topics that we touched on in the last minutes. So basically, the Ansible, the event-driven Ansible is containerized as well. So we have an MQTT connector that is taking the information from a dedicated topic on Mosquito, and it will actually take some decisions based on what is the event that is generated. But of course, now we've seen the picture. Now let's just jump for a second on what's the implementation of this. I will not go into details about the actual Quarkus implementation. The repository will be shared at the end of the slide, so there will be a QR code if you are curious and you want to go through that. It's quite, it was a bit, you know, it's a bit modular. I tried to make it as modular as possible, so I hope we will be able to just recreate this if needed. But I just wanted to show you, let me just go here. So here we have our rulebook. So getting back to the discussion that we made before, so the rulebook is something that is very familiar because it looks like a playbook, but it's called in a different way, and also has different, from the implementation perspective, it has also different keys that we can see here. So we have the sources and the rules. So the sources are actually the actual implementation of the plugin that is connecting to a remote source or a local source or whatever, and just taking the information. In my case, it's a very simple one. It's just taking a couple of parameters here. So what is the host of the MQTT broker, what is the port, and what is the topic. Of course, this can be also extended at will. What is important here are the rules. So the rules are, okay, now we are in the, we are actually in the, we have the event. Now we have the event. Every single event is, has this prefix, event of course, and based on the implementation, it can have additional keys that are needed to just go through the tree of the event itself. Usually, if we are talking about JSON messages or something that is browsable, it will be just about accessing it as if we are just going through a tree. And the important part, so the what, is the actual action that we are going to do. So it's, as you can see here, it's just about running a playbook. So it's just a very simple playbook that is just taking care of analyzing the event. So it will further analyze the event, and based on the outcome of the event, it will just adapt our temperature. So just to make you see this. Okay, so we have our basic, so our sensors are basically just, okay. So we have here our sensor data. So our sensor data, as I was mentioning, we have 3 sensors in the room and outside, and 1 sensor in the fridge that is down there. And we have, I added some humidity, temperature, and stuff like this, just to make it a bit more real. And from the fridge perspective, we have also the power consumption, the echo mode, if we have the echo mode on or off, and of course, what is the speed of the fan that is actually working in the fridge itself. And we have a fixed temperature here, so this is the operating temperature of the fridge. And this is actually, what is the sensor getting from the fridge itself? Now, let's see what we can do here. So, it's very hot outside, so we are going to just raise the temperature a bit. So it's a very simple script that is just changing the configuration of the different sensors, so to simulate a sort of change in temperature. And let's see what's going on here. So if we have any change, sorry? Okay, so let's wait here. We will have a slight change. Okay, so basically the temperature just changed, so I increased like 4 or 5 degrees, so it's a very typical summer situation where you're just jumping from a temperature to another. And here it's not happening so much at this point in time, because actually the data is starting to be transferred to the aggregator. So the aggregator is writing the data here, and we have our actuator that is actually gathering this data, and it is actually taking care of trying to find a sort of anomaly detection, let me say. It's a very rudimental anomaly detection based on some thresholds and on previous iterations. But I just added myself in this side. We have what's going on in the Ansible, in event-driven Ansible container. So what we hear, so something happened. So basically the actuator noticed that there was something that was changed in the temperature. So we had a very slight temperature change. So coming back here, looking at the log, we just received this event that has this structure. It's basically a JSON message. And it is basically, okay, there is something that is not working, so it is going through the processing part. So it finds that there is an anomaly. It just prints some information about what is the delta of the temperature. Again, it's a very rudimental detection, so it's nothing precise, but it's still working. And it takes some information from the actual deployments, changes the configuration, so it basically changed the configuration of the fridge. So the fridge was our target. And this is basically what what's going on here. And as you can see, we just seen how, and it's really nothing complex because it takes a very small amount of time to just have a good automation in place. Of course, all the part behind is a bit, of course, preparation and everything. But again, it's even looking at the code, it doesn't require so much effort to start working with events. Of course, it can be complicated as much as we want, but as you can see here, again, I'm not a programmer, so I kept it very basically, and I really hope that this was a good use case, to be honest. And just getting back here. So this was the last part of the demo, actually. So I really hope you enjoyed that. So if you have any question or discussion or you want to raise something, feel free to do that. I'll be more than happy to go a bit deeper on that.
I have a question.
Yeah, please go.
So you mentioned that we could write rules and the events. Sorry. In the demo, you showed that we could write rules, right? Now let's assume we have a huge scenario where we really want to automate a lot of things, and I'm writing, let's say, thousands of rules to manage it. But then at the end of the day, my code would become messy, right? If I want to change something, if I want to change one of my rules, managing all those rules would be a little tricky. How do you manage all these rules together in one place and make it easier for a developer to read and change it?
Okay, so basically, just recapping a bit. So if you have, yeah. So if we have multiple rules, how can we handle the granularity of managing all these different kind of rules when, especially when multiple developers are working on the same kind of automation? Well, this is actually how you would treat a very complex problem. I mean, you are not going to work on the big bunch of rules, but you can, for instance, split the different rules based on what is needed by what. So in the case of having, particular kind of events, like, I don't know, in the case of the temperature, let me say. So you want to manage the temperature, the humidity, and a lot of additional data. You can also try to split those into some smaller sub-problems, like having a dedicated rulebook that is just taking care of that particular use case. So you can also have a rulebook for the temperature and having a different rulebook for the humidity. So if you're working on the temperature and I'm working on the humidity, we can still not interact with each other, but we can still work in a, let me say, sustainable way. This is a very good question because, of course, the number of rules, but think of also the sources. The sources, it's not, we have worked with a single source, but we can have multiple of them. And each one of them can produce different events. And even the same source can produce many types of events. So, it's getting, what I would suggest is try to split it into, better manageable problems. And I think it will be a good idea to start with. Please.
I didn't get how you gather the events. So you call from the Ansible machine, or you can deploy clients that push the events.
Okay. So, the question, if I got it correctly, is how I actually gather the events. So, do we have a listener, or it's just pushed from a client deployed? Okay. So basically, the sources are just listeners. Can be listeners, so they are always up and running, waiting for someone to push. So instead, think of a webhook. So you have a sort of COD web server that is running continuously, and you have someone calling him, so you have a client. In case of a Kafka event, for instance, you have the client also on the event-driven side, because you have someone that is connected to the Kafka topic, and it's just waiting for something to happen. So you also have another client on the other side that is actually producing the event. And also, sorry, okay. Sorry. Yeah, okay, thank you. And so when you're talking with, asynchronous messaging, you still have two different clients, but it's not, waiting for something to happen. So, and of course, you can also extend this kind of thing because it's, as I mentioned, it's just about a Python plugin that you can just use, create, and reuse for everything else. Thank you. Do you have any other questions? I think you're fine. Good. Thank you. Thank you so much. This is the code for the repo, if you are interested in, and I have just one ask for you. It's the first time for me here, so please make a good use of the feedback. If there is something that you didn't like, especially you didn't like, please let me know. Thank you so much. Thank you.
doesn't work. Ah. Okay, so like this. Okay. I close the door. Alrighty, welcome everybody. It's so nice to be here after 3 years and meeting finally everybody in person. I missed it so much. My name is Antonio. I'm an engineer for Red Hat, where I've been working for the past 8 years, taking care of containers, OpenShift, and now Peter Falls, the Edge, right? So today we're going to talk about resiliency at the edge, who we are. So there I wanted to put a team picture, but I basically meet my team now. So, we've been working together for 3 years, but no picture together in real life. So we are the team building RHEL for Edge. We also maintain Fedora IoT along with the upstream community, and we developed all the technologies for the edge, like FDO, Greenboot, which is the topic of this presentation, and all the parts in Image Builder that makes it possible to actually build RHEL for Edge. I lied. This is my team. You can see a couple of funny faces, like Micah's there. You gave permission to share this. So this is my amazing team. So as I said, we built the operating system for the edge, or that's what we call it. And RHEL for Edge is built using Image Builder. It can be Fedora and RHEL. The team focuses on both in the day-to-day with a push to do upstream first and more upstream in general. All of the RHEL for Edge system is based on OS 3 and RPM OS 3, and it runs on those tiny devices like the Fitlet 2, the Intel NUC, and it's made of a curated package set, things that we only need at the edge, or things that we don't need and we just remove. That's the last line. It's lean and secure. You don't want a huge attack surface. You want the system to run with minimal amount of RAM and CPUs. So that's how we've designed it. So before talking about resiliency, the way we build RHEL for Edge is we create an OS 3 container commit with Image Builder that basically just build the OS 3 layout that then we serve as a remote repository to Image Builder. Image Builder, what it does is, with that simple blueprint, that creates the OS 3 commit, and then when we serve that, we can build an installer, like Anaconda or the simplified provisioner. You can build a raw image. You can build pretty much whatever you want. Kudos to the OS build folks here. I've seen Achilles somewhere, yeah. After you have this artifact, like can be a raw image, can be an installer, can be Anaconda itself, what we're gonna do is basically flash the OS to a device. That's the provisioning part, which I have another talk after this to talk about. And as part of that, as part of the flashing or provisioning itself, there is some sort of tagging that you want to do to the device in order to later identify it and things like that. And then with these tiny devices, the edge use cases is you provision the device with an operating system. The analogy here is when you go and buy a Windows laptop, that stuff goes out of the manufacturer with Windows pre-installed, but it's not activated. So this is pretty much the same. You have a bunch of devices all provisioned with RHEL for Edge, and then at the end, you're going to ship those anywhere in the world. This is IoT, so this stuff can be a light bulb, can be a sensor at the top of the Everest, anything that is tiny or not really tiny that we don't have easy access to.
It doesn't even need to be in the world. It doesn't even need to be in the world.
Exactly. Yeah, it can go to space too. That's what Peter is saying. And then once it's at the Everest, somebody's just going to power it on, and it does onboarding,
Some of my team members are going to do the onboarding part of a RHEL for Edge system, so make sure you sign up for Irene Esterido's talk. And at that point, this device is at the top of the Mount Everest. It's up and running. All is good, sending sensors data back to the I don't know, main data centers or whatever, crunching data on actually there on the mountain. So whoever shipped the device to the Everest, like actually walking up there, just power it on and go back to the office. Like that is easy, right? Now this is day 2 operation instead. So the device needs an upgrade. So that is the blueprint that creates an upgrade, and it's still an OS3 container commit that we build using Image Builder. In that example, I just added Nano and that file. And then we're going to serve this commit, build the upgraded OS3 commit, and then what we're going to do is basically just run RPM OS3 upgrade and then reboot it. Once we run RPM OS3 upgrade, we get this kind of output, and it says just run systemctl reboot, and everything is going to be fine. You're going to be booting into the next version of the operating system. This is cool, right? So what can possibly go wrong with these scenarios, basically? So, upgrades don't always go as planned. So probably the worst nightmare is something like this. Like you have a device at the top of the Mount Everest, and it's like, oh my God, I can't connect to it anymore. That may be an issue, right? So there are a couple of solutions for this. The very silly and simple one is to send somebody to the Everest. It's probably expensive, tiring. For those who know, that's Noemi. My partner, she gets sick every time. So and that's not even the Everest, of course. It's super sunny there. So somebody has to go physically there and debug the device, which you can imagine is probably not going to happen. It's really unlikely. You have these tiny devices everywhere in the world or in space, and you want these to run smoothly, to upgrade, to continue working, to run the applications that have been deployed on these devices. So everything has to be smooth. So this is not going to work. Poor Noemi, this is not going to work. So that's when Greenboot came into the picture. So some history here. Greenboot it's basically a tool that makes it possible in an RPM OS3 and OS3 system to go back to the previous deployment if there are any issue in the upgraded deployment. I'm assuming some familiarity with RPM OS3. Basically, you have 2 deployments at all times, and when you upgrade, after you reboot, you go into the new one. With Greenboot, it's possible that if you add some check and the new one doesn't work or doesn't behave the way you want, it goes back to the working deployment, so that any upgrade that goes wrong, you have a chance to revert it and then maybe debug it further or ship another upgrade and things like that. So Fedora has been created, Greenboot has been created as part of the Google Summer of Code in 2018. 2018? Yeah. The whole idea has been created and led by Peter Robinson here. Christian Glombeck was the intern working on Greenboot at the time. Also, Dusty Mabe and Jonathan LeBon helped him as mentors too. And again, this has been part of Fedora IoT because Peter saw the need to have unattended rollbacks on these devices, because otherwise, again, you need to send Noemi back to the Everest. Unlikely. The whole project has been designed around RPM OS3, because of course in a normal system, it's not as easy to ship an update, roll it back without any disruption. That's also unlikely. And it has been made to work with Grub. So right now we just support Grub, but any UEFI, boot system or whatever can be made to work. Like if you have ideas, if you want to contribute, feel free. And so with these 2 pieces in mind, RPM OS3 and Grub, Christian created the very first implementation in 2018. And so how Greenboot works is pretty easy. Somebody runs RPM OS3 upgrade and systemctl reboot. When RPM OS3 upgrade is called, Greenboot sets some variable in grub. And after that I'm going to explain in a little bit, and then we reboot. So at the next boot, green-boot starts a couple of health checks, what we call health checks, and based on those, it's going to run a couple of boot status script, meaning, okay, the deployment is okay. Now I'm going to send an email to an administrator maybe, or somebody saying everything is okay, or worst case, the upgrade doesn't work and we need to roll back. Yeah, the last one is rollback can also happen. Maybe you can have transient failures. So you may want to retry a couple of times, or how many times you want the new deployment. Maybe it's a network hiccup or something. So in grub, this is how Christian made it work, and how it is today. There's Christian. It's outside. It's basically leveraging a couple of grub functionalities, like setting variables. There are two main variables that drive all the green boot processes. The first one is the boot counter. The boot counter is set when the upgrade is done, but before the reboot happens. Once the boot counter is set and we reboot, every time that the deployment fails, we're going to decrease it until it's negative. That's the signal that we need to roll back. So hopefully it's super easy. And the other variable is boot success. Before the upgrade, we set that to 0, and then if the new deployment works, we're going to set that to 1. Those two variables basically drives all the green boot operations. We shipped some template in grub.d just to make all of this logic works as I've explained it. Hopefully it's clear. Two main one, it's a fallback counting, basically just decreases the boot counter, and the other is boot success. It's 0 before rebooting. It's reset to 1 once the upgrade goes well. This is all green boot. Green boot is a couple of scripts and many, at this point, systemd services. It has a state machine-like operation model, so every time it checks the variables and where it is at that moment, and based on that, act. So the first service that we have is the greenboot grub2 set counter service. This is the one that is directly wired to OS3, so that when OS3 runs an upgrade, well, you run an upgrade, and OS3 takes care of that, it's going to fire that service. Greenboot intercept it and say, okay, it's time to set boot success to 0 and boot counter to whatever the retry, the actual retries you want to do for that specific boot. And then there is greenboot health check, which is it's the main service. It's ordered before boot complete.target. And what that does is running the custom health check that everybody can actually add to greenboot in order to say this deployment is good, this deployment is not good. If it's not clear, I'm going to show an example later with a demo so that it becomes really clear. So if the health check service passes, boot complete is reached as a target, of course. And then there is another service setting the success variable in grub and unsetting the boot counter grub variable. And then if everything goes well with the new deployment, there is a further option to run additional script that's in the green D directory. Again, it can be an email to Peter saying, okay, the deployment is good, all good. Deploy it to a space. If it fails instead, there is the whole rollback mechanism run by redboot how to reboot.service. And it does, as the slide says, a series of checks to determine if there is a requirement for manual intervention, because that can happen too. Otherwise, it just reboots the system and try again if reboot has been configured to retry. And when when the health check fails, then the red.d scripts run, and at that point, you can still send an email to Peter. At this point, you have a filter saying, okay, no, this deployment doesn't really work. You don't want to boot there. Maybe it's, create another one.
You wouldn't want to send it to me anyway.
I could, I'm going to send you email. Yeah, so this is the very basic directory structure for greenboot itself. as I said, the required.d script under etc greenboot check is the one with scripts that must pass. It means that if you boot into a new deployment and any of this script fails, then the whole boot is marked as not good, and what greenboot does is either retry or just rpm-ostree rollback to the previous deployment. The wanted.d script directory is it's a directory that holds scripts that may fail, can be failures that are okay to happen in a new deployment, but then maybe, network, for instance, probably better in required.d, and then in wanted you have something else, assuming network has been working, to further debug. And as I explained, green.d and red.d are just boot status script. If it's green, run this. If it's red, run the other. Yeah, this is the configuration. I know it's pretty slim, but this is the configuration variables that we implemented in greenboot. The max boot up temps, it's the one that takes care of rebooting until that number, and the other two are part of a script. Yeah, Yarrow watchdog. But I'm really not going to get into that because the watchdog is probably a whole new topic. But those are the ones that we support today. The first one is probably the most important. And in my demo, it's configured to 3, so you will see the virtual machine rebooting 3 times. I don't know how much time. 48, so 10, 50 minutes? Okay. This is all the health checks are scripts, bash scripts. I know it's bad. We're working on that. Not necessarily bad. And this is what you actually write in order to have something run at the next boot and then mark the boot as a good boot and then keep the deployment, or something that has to be rolled back. This is bash, pretty easy. If there is that file, we're going to fail and we're not booting into that deployment. If there is not, everything is good. We stay in the new deployment. And the demo. I have a machine somewhere. Okay. Can you see? Yes, awesome. So this demo is basically demoing what I've been saying, and we're gonna, I've built already the upgrade, and what we're gonna do together is run the upgrade and reboot. I didn't trust the network to do all of that, so I did this in advance. You can see here that, so right now I'm at this version, market 5.7. This is normal rpm-ostree things, mechanism. So we are booted into this deployment. I've built instead an upgrade. I've built an upgrade based on this slide, this one, where you can see that I've added that file, which is the one that is going to fail. It's easy. It's really silly as a demo, but it explains how this works. So the new upgrade is going to contain that file that it's going to make the new deployment fail. So really easy there. I built that using image builder, and if we follow rpm-ostree commands, I can ask for the upgrade. And you can see we're going to go and upgrade to 6.7. There is a new package added. This is how S3 works. It's just nano, if you remember the blueprint. And so now what is left to do is just reboot the system. Oh, actually, we need to upgrade. Does it work? It works. So right now it's upgrading. You can see we added the nano package. So this can be a normal upgrade during normal operation at the Mount Everest. So somebody needs something, a new customer application, I don't know, new sensor data, or a program to send back sensor data, whatever. It can be anything. So at this point, what we're going to do is just systemctl reboot. what this does is basically going to try and boot into the new OS3 deployments. Hopefully it's visible, but it's not really important. There were 2 boot entries that have been shown. There is some issue there. Oh, time. Yeah. Okay. Yeah, so I'll start from here since this is not going to work anymore. I prepared for this, but this can happen. So after I rebooted, what was going to really happen, I'm sorry for this, is 2 boot entry were shown. Those were the old deployments and the new deployments. So we were trying to boot, this is the new deployment. As soon as you are in the new deployment, Greenboot runs, check that else check that I've shown you before, basically checking if that file is there. And if it's there, Greenboot is going to run and reboot the system. And the next boot for 3 times, we're going to still have the 2 boot entry where we retry the new deployment. After that is done, and we are at -1 with the boot counter variable, then we're going to just roll back to the old deployments. It's super silly, it didn't work. But yeah, so that was basically the demo I wanted to show. I'm sorry for this. And 53. All right, so yeah, so what's next for Greenboot? We have a couple of points that we wanna enhance in the future. Not everybody like bash scripts, so what we're gonna do right now is rewriting the core in Rust, and then perhaps enhancing the API so that everybody can drop any executable and base it maybe on exit code 01, things like that. Anybody can write their own health check the way they want with the programming language that they want. What we're going to do next too is having better RPM OS3 integration. Right now, we're basically hijacking the way RPM OS3 does the different boots, but we want to do better there, starting in Fedora IoT. We already started talking with the CoreOS folks, the folks maintaining RPM OS3 too, to actually do that. There are some hiccups with Greenboot itself and RPM OS3. The biggest one to me is that etc is writable. That means that if somebody messes something up under etc while a system is running and then run an upgrade that wouldn't make the Greenboot health check fail, then Greenboot is gonna just be fooled by that, saying, okay, this is actually not booting and it's not green. So what it's gonna do is just roll back. And this opens for all sort of attacks too. Maybe you're upgrading because there is a CVE, but again, can be fooled and it's not good for security either. And lastly, we have some actually live users of Greenboot. The most notable is Microshift. They are implementing health checks to make sure that they can go back and forth with Microshift itself, which is OpenShift and things like that. So this is the future of Greenboot. If you have, again, any idea, I have a couple of links here, starting from the actual repo on GitHub, and then the whole explanation by Christian Glombeck, who created all of this. And then I dropped a link also to OS Build Composer, since the way we actually build all RHEL4Edge artifacts in RPM OS3, of course. On time? Yeah, okay, questions? Yeah? Yep, yes, Peter.
How do you deal with attack vectors that may force a rollback to get access to CVEs in a platform?
Are we handling that? We're not handling that.
No, we're not.
Basic. So this is, repeat the question, Peter. How do we handle?
How do we hand forced rollbacks via an attacker to enable them to then attack potential vulnerabilities that have been fixed in the upgrade?
Right. So the questions were, Peter already knows the answers, and the answers that we haven't fixed that is.
What was the question?
Yeah, the question is, how do we prevent somebody from actually forcibly rolling back to something that isn't patched, right? Maybe we are upgrading to something that fixes a CVE, but then with something like this, maybe we are forced to go back and then introduces, of course, a vulnerability in itself. We're working on this. There have been a couple of ideas too. Probably the RPM OS3 integration is one of the things that we first have to take care of in order to. It's complex. It's a complex topic.
This may be a controversial question since this is a Red Hat conference, but what are your plans on supporting other ways of delivering software other than RPMs? Because I've been more than once in a situation when a new release of a Docker container or a snap broke an edge machine.
Okay, a RHEL for edge machine? No.
Sorry?
A RHEL for edge machine?
No.
Just a general machine.
So
let me repeat the question.
The way we deal with, so that's unrelated to Green Boot in general. Yeah. The way we deal with that is you run that in a container on the base operating system.
Okay, but there are scenarios, I actually had one, when a new version of a container can, affect hardware or other, or affect the machine in other ways. So.
Yeah, so we would roll back the container and we would deal with that.
That would be independent of
the system, yes.
We can deal with that within like the health check scripts.
Yeah, possibly.
Okay.
Achilles?
Yeah. To go back a couple of slides. So the NC is writable thing, right? Full in Green Boot. It just made me realize that is there room for a check where before doing the reboot for the upgrade to know whether the rollback will work, because maybe a configuration change doesn't make the current state
broken,
and then you're in a sort of flip-flop state.
So
is that something that might happen?
And the safe thing that we used to do when I worked in OpenShift with the MCO was any change under etc would, and of course we can do that in OpenShift because the hardware is free more or less. Basically every change in etc triggers a reboot, so that you make sure that at the next reboot, if it's working, the change itself, beside. Exactly.
Yes, but we don't have the ability currently to roll that back, and we're looking at how we can have almost like a config layer and work it in the same way. Because if you change, say, like the example I always use is if you need to change, say, the network provider out on the edge, and that is like a three-step process where you may need to change a network interface, a DNS service, and a VPN service to be able to connect to and retrieve an update. If any of those three fail, you can't upgrade again to fix the problem because you can't connect to the update service because you've got no network. And so how do we deal with that? And that we don't deal with it very well, and it's complicated, but it's sort of like on the
And besides RPM OS3 and Fedora, there have been a couple of solutions like using BetterFS snapshots to say, okay, this is just a config layer, as Peter said, which is different from RPM OS3 config layers, OS3 config layers, but the solution is probably lays there.
It's not really a question, but more a comment on the tamper-proof thing we were talking about in the last question. But one of the things if people are interested in that area, they should follow. Because Alexander Larson has been working on something called
ComposeFS?
Yeah, but we're not fully aware of that.
Yeah, I know. It's more for the audience. But I'm not sure if it solves the case of moving into an older commit, but it does strengthen the verification all the way up to the commit that you're moving into. It's just an interesting area.
Yeah.
If people are interested in that whole time.
Yes. So if the comment was around ComposeFS. I don't know if you heard, if everybody heard, can be a potential solution to this. If you don't know what some pieces of ComposeFS, yes.
When you were showing the demo and it hanged out, I assume we would did like this and give up after some time and
Yeah.
roll back, or
well, except in that case, because Unfortunately, I think the machine that I was using runs a RHEL version that had a bug. So that was basically just retrying forever, because that's how the ignition service is made to work on first boot. It wasn't first boot, that's a bug. Otherwise, yes, if there is anything that hangs and at some point reboot, then reboot will still work.
So I don't understand what's the difference here. Why?
This is like the ignition fetch routine is running forever, so that never ends.
So the system would not detect it?
Yeah, exactly. I mean, that's a good point. Perhaps something to consider into new features about Greenboot, maybe. Hey, Tomasz.
Yeah, Leo, very nice talk, thank you. Can I use Greenboot on my laptop, for example, if I'm running ROI?
If you're running RPM-OS 3, like, I don't know, Silverbrew, ROI, yes. It's very bound to how RPM-OS 3 works. That's it? I know.
The only integration point, from what you described, the only integration point between Greenboot and RPM-OS 3 is the place where the flags are set to red.
Yes, the integration point is. Oh yeah, the only integration point between Greenboot and RPM-OS 3 is when the grub variables are set. Yes, right now, what's next? There is better RPM-OS 3 integration. That means we're gonna make that link more robust and not just rely on the OS 3 finalized staged that run after somebody run RPM-OS 3 upgrade, because that can be flaky too. Sometimes, rarely, you can miss that too.
When this work with the improving integration with RPM-OS 3 would prevent that, but you could also see a number of critical packages that work with that, so customer decides will require a root and will actually require a rollback if there's an issue. And I guess the only package that we have that currently support is a kernel that we can install in Nora. So you could have a script that's in the kernel RPM that would set these group environments and enable to network people.
Perhaps, yes. Yep. Anything else? On time? On time. Thank you. Welcome again, folks. Speak louder. Okay. Welcome again. My name is Antonio. In this next talk, I'm going to talk about device provisioning at the edge, specifically what the team did over the past 2 to 3 years to make it possible to provision a device for the edge. I'm an engineer at Red Hat, working for 8 years. Right now, I'm working with a team of 8 engineers on RHEL for Edge. This is the slide, like somebody of you already seen it. I've already seen it. We build RHEL for Edge. We take care of Fedora IoT 2, along with the upstream community led by Peter. And we develop and maintain all the technologies that make RHEL for Edge, and Fedora IoT, of course. For instance, the FDO, Secure Device Onboarding, Green Boot that I've shown earlier, and the simplified provisioner, which is the topic of this talk. Not in picture, unfortunately. And so the agenda for this talk, we're going to talk about how do we provision a device at the edge, what the requirements are for this process, or at least what we've been gathering in the field, and based on experience by talking to many hardware partners and vendors too, and which tools have we developed in order to meet these needs, and what we've learned so far, and what's next. So at the beginning, I really struggled with all of this. Peter Robinson has been preaching this division in the flow. So at the left side, you have the build phase. The build phase is when you actually build RHEL for Edge or Fedora IoT. That part for us has been done through Image Builder. You basically specify the package set, some configuration option, maybe some files to inject, maybe some kernel arguments to tweak, and then what you end up having is an artifact. This artifact can be a raw image, compressed raw image, can be an installer like the simplified provisioner, or it can be Anaconda itself, can be an MEI, anything that boots can be made at this phase. So in this phase, you're not playing with the hardware, with the device, you just build the artifact that you want to put on the device, or that you want to install with. Then this topic is about the middle layer, the middle balloon there, and it's the provisioning part. The provisioning part is the part where you have 10,000 devices and you want to effectively and efficiently flash an OS onto the device and make sure that it is ready to boot. And ready to boot here means so many things. The provisioner or whatever provision the system can just flash the image onto the disk, or it can run and integrate with things like secure device onboarding, can talk to the hardware for security sensitive things like talking to the TPM, storing keys, all of this, all of the things that has to be done at provisioning. The analogy here is, for me at least, the way I understood it, is the Microsoft part of the word. I know this is a Linux conference, not pertinent, but still. Microsoft can ship pre-built laptops that already have Windows. So they provision them very early. And then they ship that to you, you power them on, and they onboard. Usually you have a Windows key or something, connects back to the central Microsoft data center and says, okay, this is actually a system that has been registered with us and it works. So the provisioning part is usually done at the manufacturer, where you have, again, thousands of devices. You want to install the very same image of the operating system onto them and just them simply ship them or sell them. And then there is the onboarding part, still a reference to the next talk in this room, because it's about the onboarding part for us that is done securely by two mechanisms mainly. We use FDO and ignition, and Irene and Sarita, we're going to talk about that later too. For this talk, we're focusing on provisioning. So at the beginning, we tried to gather some of the requirements of what this process should have. And the very first one was it has to be unattended. Nobody has to, interactively type on a keyboard or watching a screen, like zero touch. Yes. So we don't want that. We basically want somebody, for instance, to grab a USB key or boot the system, the provisioner remotely, and just install on a fleet of devices. And the number here can go pretty high. Like, again, we're talking about thousands of devices that you want to flash in the very same way with the very same base operating system. And so the first requirement for this provisioning part was unattended, hopefully fast, which is somehow different from normal installation and installers where you're actually there, clicking the mouse, selecting the disk, maybe doing something else. You want the provisioner to go as fast as it can and to be able to scale to thousands of devices and just works. Just install the system, ready to power on. And that's why the second requirement here is should support remote installs. At the beginning, we were talking about Pixie and other remote install mechanism. Pixie isn't secure. So what we've settled up was just use UEFI HTTP boot. So that has been a requirement from the beginning for us. You basically have a web server that serves the initRD, the kernel, a couple of kernel command lines to drive the actual installation, and then install it, or you provision it. And yeah, the other requirements are similar to this. We want to be able to tweak something into the installation or the resulting system. An example is the console kernel argument. Maybe you have thousands of devices where the kernel, the console is on TTIS something, or TTI something in general, and you want that to be the same over the same hardware. So the provisioner should support something like this. Partitioning is also one of the requirements that we got, partitioning and injecting files in directory. We're not doing that right now at provisioning time. We're doing this mainly at build time, but we're going to find a solution maybe later in the future to also do this at provisioning, because we've been asked, maybe.
It's a hard problem to solve.
Yeah, that's why I'm just mentioning.
Especially on the edge.
Exactly. I mean, I'm listing this there because those have been discussions and points that we've taken from various parties, customers, partners, users, the Fedora IoT community, maybe. So we have these requirements. And as I said, these two specifically are done at build time. Interact with the hardware like TPM, that's something that, of course, if you have an installer booting, that's doable. So we've been able to do this just fine. And it has to be secure. Main definition of what this means for us, even just interacting with the other TPM was enough. And yeah, so the idea that we came up with was having a, Peter called this a minimal tiny initRD installer at the time. And what that meant was just create an initRD, pack something in there, like a kernel, initRD, some tools to actually write the image onto disk, and any other tool that we need for this. And then make it also bootable over HTTP boot. And of course, flashing an image onto disk. That's the very first requirement. You have an image, you run the provisioner, you want to provision the device with that image. And the other one, as I said, that we come up with was the ability to inject kernel arguments, interact with onboarding. As I will show, we made the simplified provisioner, the provisioner that we use as a Dracut modules, and that means that it's pluggable. We have a couple of other Dracut modules like the FDO1, which is part of the onboarding that we can, quote unquote, easily plug in. So the whole system is made pluggable by using at least Dracut for us. Just to support encryption, right now this is also, again, the part where we already built the image encrypted. But again, in the future, that may change. Like, we can do live re-encryption at provisioning time. Maybe that will be a thing. Right now, we're doing that at onboarding, though. And we're building the image already encrypted. And lastly, this is one of the things that we get tasked every time. The installer should extend the raw image to the full disk capacity. So we have a raw image, maybe it's compressed. Uncompressed, it's 14 gigs, something like that. we DD the image, we basically flash the image onto a disk, which is 100 gig, for instance. And at that point, what we've been asked is, okay, but I need to grow that root file system to take on the full disk space on my device. Because of course you want to leverage the whole, hardware that you have. And so this provisioner has to support something like this. So we initially created the simplified installer, but that was causing a lot of confusion. Peter is already looking at me like, you shouldn't say that word. And that's when we called it the simplified provisioner, just to distinguish between the phases. So this is the simplified provisioner that we came up with. We're still calling it simplified installer somewhere in the code, especially in OS build, but we are not struggling, but we're working towards removing that, wording, basically. And it's, yeah. And as I said, it's a tiny ISO. Like we've been able to pack everything we need into an ISO that contains just the kernel, the initramfs, and the raw image. So there is no real system running there. We boot the initramfs, the kernel, we have the image, we're going to work with that. All of the simplified provisioner, as of today, is driven by Dracot modules and systemd services into the initrd. Basically, this allowed us to, again, plug as many pieces as we want to control the flow of the provisioner itself. For instance, we flash the image, and then maybe we want to run FDO to do other stuff. Maybe somebody wants to mount the root file system and inject some certificates, things like that. By using Dracot modules for us, this was the way to make this possible. And the reason for having an ISO, like a normal ISO 92 something, is because all of these components, like you can actually unpack the ISO, and then you can have this component served over HTTP with HTTP boot, and then this stuff can just boot and install the system and run the initramfs and the kernel. So what we need to do, of course, is before all of this, once we build, at the point we build the simplified provisioner, we of course need a raw image to work with, because that's going to be the golden image that we're going to provision over 10,000 devices, for instance. So we need to build this raw image. We're using Image Builder again. And what we're going to do, as I shown in the other talk, is first build an OS3 commit that contains the base system. With that, we're going to just create a raw image. And this is when partitioning and encryption are taken into account. So at this point, Image Builder is going to create the raw image out of an OS3 commit for us. What we do with this image, we embed that into the ISO so that the simplified provisioner code can use it, uncompress it if needed, and flash onto the devices. Okay, so the way we produce the installer is, of course, the provisioner, as the slide is wrong, is through Image Builder again. We have created over time a couple of stages. That's how Image Builder works, by having stages that do something onto a rootfs. For the provision, for the simplified provisioner, the team created a bunch of stages that we put together in order to basically have the resulting ISO that you can see in the image. What we do is, so Image Builder is basically creating the raw image. It's compressed, so it takes up less space, and then it makes it bootable via ISO Linux, FEI, and everything else, and then embed also the initramfs and the kernel. So all of this for us is done with an ND blueprint and command from Image Builder. Yeah. So now onto the requirement on how do you write the image to the disk. Like you have this nice ISO, there is a raw image, and now what we need to do is actually writing that on the disk when we run the simplified installer. So for this reason, we have chosen to use CoreOS installer. For those not familiar with it, it's a project from CoreOS, from the CoreOS team that is widely used in OpenShift, and it's basically the way to flash an image onto a disk. In its simplest form, that's what it does. But it can also do something else. It supports embedding ignition. as I said, support compressed raw images, so you can embed a raw image that is compressed, and then when it writes it down to the disk, it gets uncompressed on the fly. It's a huge win for us, of course. We can keep the ISO itself more concise, basically. It has encryption support. CoreOS installer can be run as a Dracut module itself. The team created the CoreOS installer Dracut project, and that's a way to run CoreOS installer in a Dracut module. And being Dracut and being just command lines tools, we were able to integrate all of this using systemd, basically. That's the framework that we're using. It allows us to order units and execution the way we want. So we're using systemd there too. Yeah. So now CoreOS installer is really neat, and the way we made it work, it's even so, I think, because the whole execution is driven through kernel arguments. And now this is again neat, because if you want to boot this provisioner remotely, then you want to be able to drive the full provisioning through something like kernel arguments, because every device is going to come up with this kernel command line and it's going to execute this. And so we were able, by using a systemd generator, to leverage the systemd generator and just parse the kernel command line and then say, okay, we want to install the image onto DevVDA. This is a virtual machine, but maybe your hardware has DevSDA or something. So if you have 1,000 devices, all these you want to install on DevSDA, you can configure this via kernel arguments and then boot this via HTTP boot so that every device is provisioned in the very same way. There are other things that can be tweaked, like where the image file is, can be remote. Actually, for HTTP boot, you want the image file kernel argument to be image URL, so you can CoreOS installer can optionally fetch the image from a remote location every time. They may be slower, but it works. It can be made to work. And so this is how we achieve conditional execution in a nutshell. So yeah, this is basically what I said. Apart from parsing the command line just to derive the execution and configuring the installation device, we can also tweak how we behave post-install. Somebody can install provision the machine, and then maybe you want to reboot. Maybe you don't want to reboot. Maybe after provisioning, you want just to get the hardware, pack it, box it somewhere, and then ship it to the others. So anything can be this flow can be tweaked by post-install kernel arguments that we provide. Another thing that CoreOS installer Dracut does, our Dracut module, is mounting the ISO, so that if the image is local to the ISO, we're gonna have the image available into the initRD so that we can flash it onto the device. And then at the very end, this was the systemd generator for CoreOS installer. We're just gonna run the CoreOS installer service, which is just a command line saying CoreOS installer -- install, and then the target disk, post-install behavior, where the image is, all of that. So we've been able to achieve this with a systemd generator, basically. And as I said, the CoreOS installer service, this is just a snippet, but at the end, it's going to just echo a command, and then it's going to get executed by systemd itself, and it's going to run. I hope this time the demo works, because it's really tiny, so you can see the actual command line, CoreOS installer, install, and everything else. Yeah, so all of these kernel command line options can be configured by an image builder. So I'll show a couple of blueprints that that we use daily to build the image. So you can configure the install device. You can configure FDO and ignition. There are various options. For FDO, you can configure certificates. You can configure the manufacturing URL and other things that we've been explaining later at the FDO talk and ignition talk. For ignition, you can attach a kernel argument to say this is where you're going to fetch the actual ignition configuration. Again, you can configure the target disk via blueprint, all of this together via image builder. As I was saying, this also integrates very well with FDO, which is secure device onboarding. And I'm repeating myself, but FDO is also a Dracut module, so we can order it after we write the image to the disk. We can have FDO run and do whatever it needs to do with an installed system, like registering keys to the TPM and other things that at provisioning we do with FDO. Then, so for this demo, like I'm using a normal virtual machine. What I've done is I've created a simplified installer based on RHEL 9.2 in this case, but all of this is coming to Fedora really soon because we got the latest bits of everything we need. So expect it in the next month or so. All of this can be tested. It's pretty exciting. As you can see, Peter laughing, smiling actually. So all of this can be tested with also Fedora. And so I've created a simplified installer using this blueprint. And as I was explaining earlier, like you can see, I can customize the installation device. This is a simplified provisioner meant to install on the dev VDA disk. That's usually QEMU and like. And then what I wanted to do also was add a first boot kernel argument for ignition, so that the first boot of the system also runs ignition. So this is really easy to digest and grasp. It just follows the image builder blueprint options. Another thing that I can show is also the FDO blueprint. Well, the FDO snippets in the blueprint too. You can see we can configure a bunch of options for FDO itself. In this very simple case, we configure the manufacturing server URL. Maybe in a factory you have 10,000 machines, one FDO server. You create a simplified installer for that server, so you can have the very same image that installs on 10,000 devices all at once by just building this image. And then there are a bunch of security sensitive options too. This example is running insecure for various reasons, but we're not building this. This is just to show that there are aspects and pieces of the blueprint that are made just for the simplified provisioner. And this comes from the integration we had in the past with the image builder folks. Really? All right. So it seems I have 10 minutes left. So what I'm going to do here is run a simplified installer provisioner, sorry, Peter, to install on a virtual machine. You can see somewhere that no, it's I don't know. It's RHEL.9. Actually, it's RHEL.3. So you can see here I have this image. This image unpacked, you have already seen it, just the FEI directory, images with kernel and initramfs, the ISO Linux standard folder, and then the raw image. So if we go back here, and this is the simplified provisioner booting, and you can see the very same similar configuration kernel options that I've shown in the slide. So we're going to install to dev VDA, and the image file is run media ISO. That is something that CoreOS installer Dracut itself is going to mount for us, and then CoreOS installer can install it. So if we boot these, at some point it's going to, in a moment it's going to show. I know this is tiny. Hopefully everybody can see that, but you can see right at the first line, 664, that there is just a normal command line. It's CoreOS installer install where dev VDA, as we've configured, and the file is there. So the image file, the compressed image file is there. Then there is insecure too. I've explained just for demo purposes. You can see all of this went unattended. I just I just edited the kernel command line just to show you, but otherwise it's like 60-second delay, and then this thing is gonna boot on itself. It's gonna run unattended. At this point, is still writing the image to the disk, and you can see at least, this is a virtual machine, so it's pretty fast. But we've been testing this on Fitlets, in other devices, like I think Intel NUCs too, ARM devices too. So it can be slow depending on the actual hardware that you have, but in general, it's a fast process. And you, yeah. So this now it's going to reboot into the actual RHEL Edge system. This is not really important. What I wanted to show is that the whole process can run unattended. It's pretty fast too, which was one of the requirements that we got at the beginning, and it's really tiny, just an ISO. You can put it on a USB stick to install manually. You can boot from the network in order to streamline this provision. So, what we learned so far, and bear in mind we're still learning. Requirements are coming probably daily, depending on who we talk to, what their actual needs are. So what we learned so far is that many of our users / customers don't want to use raw images, and this is legit to some extent, although raw images buy us something like security, like IMA, and things like that. So we're trying also to be opinionated into this whole process. We're saying this is probably the best way. It's a bit arrogant, but trust us. Like depending on the various talks that we had.
In a lot of cases, it's not that they don't want to; they don't understand why.
Exactly.
And it's changing their process.
Exactly.
And it's an education process of why.
That we need to do. Exactly. And so they just want to use. They're used to have an installer like Anaconda. They go there, they script that with kickstarts. If you're familiar with that, Chad is definitely familiar. So you script that, you want just an installer, you use the installer on a fleet of devices, or that can be also be heterogeneous, so like even different too, and they want to have the logic to derive which system it is on the kickstart itself. That is cool, that works, but again, having something like a single raw image that can be FS verified and all the security mechanisms that can be done, it's what we're saying is better for security reason too. But as Peter mentioned, it's an education process that we need to do with the customers and with users and the community to help them understand this is definitely a better way.
Making decisions on a device-by-device basis on the edge is slow, open to security attacks, open to problems because you basically are artisanally creating every single device to deploy rather than having a guaranteed identical device across tens of millions of machines. So
it's an education process that this is what we're fostering basically right now. This is probably a good way to provision your edge devices. And as I said, if you don't have a raw image that is already packed as a whole, things like IMA and other security sensitive things and processes do not really work. It's very difficult to make IMA work with Anaconda. There have been talkings, but we're not there yet, and we probably never will be for Anaconda. So this make it easier, or at least this is what we've been told. And then the other things that we've learned is that many people and users and customers want to have partitioning at provision, at the provisioning time. Again, they're used to have something like Anaconda where you can actually script the kickstart and say, I want var here, I want etc here, whatever. You can use your imagination there. And that with the simplified installer, what we do is basically pre-partition the raw image. And so we're gonna tell you this is the layout that mostly works. If you wanna tweak it, use the image builder blueprint, and then you can have var on a separate partition, and again, use your imagination there. You can do whatever you want. For partitioning specifically, there are a couple of areas that we thought about that we can do this. One of it is Ignition, although Ignition does partitioning live on first boot. but it's often pretty much expensive. Meaning, right now OpenShift uses this, but of course OpenShift doesn't have any resource limit. They can have like 32 gigs of RAM, they can have tons of CPU power, and this doesn't work, of course, for the edge. Maybe for some hardware works, but you know, if we
also, like, you can't get OpenShift in the data center. You pretty much got guaranteed power, guaranteed network bandwidth, all sorts of other things like that. On the edge, like if you lose power halfway through partitioning, that device is toast, and you've got to start the process again. And so there's a lot of factors on the edge, network bandwidth, machine resources, various other bits and pieces that make doing things on the edge without a human to interact with, so literal zero touch, is very complicated. And the more that you can take out of that and do it the image build time, so that when you're provisioning the device, you've got minimum viable decisions that need to be made, which means minimum amount of things that can go wrong, the more likely you're going to get a successful machine that you can then sort of customize more so with something more reliable like Ansible.
Yep. And yeah, so at the end of the day, leveraging Ignition in OpenShift is okay, as Peter explained. For us at the edge is probably a no-go to begin with. Ignition can do root reprovisioning, so it can completely change the layout of the file system on the disk. In OpenShift, that's fine. At the edge, not likely. Then, so what we came up with was maybe we need to support partitioning for the raw image at build time. So that makes sense. That's something it's on the roadmap already. Maybe you can have a blueprint option just for the simplified installer to, well, not for the raw image to partition it the way you want. Again, maybe you want var on a different partition. Again, as I said, we can look into on-the-fly reprovisioning of the file system, although that's tricky. Or we can do like first boot reprovisioning. Maybe we can optimize Ignition itself to avoid, I don't know, reprovisioning a 100 gig root file system, because that would be impossible to fit into memory too. So those are just, scenarios that we're gonna run through and think about. The last one is something that we've been talking in the past. We didn't get any traction. We're at the conference. If you like the idea and want to contribute, that makes sense. Right now, the biggest thing that we've been told is, how do I test it? RHEL4Edge and Fedora IoT easily. I don't want to build the image. I want to have, something that boots and I can just navigate into it and understand if it fits my needs. So right now we don't provide the live image, but if there is any interest, traction from the community itself, we can also explore that. And that is meant like the /fcos, star fcos systems do provide a live image so that you can actually jump on the system before installing it, maybe create a template of the installation that you want to produce with CoreOS installer, and then just boot that. So that is something that's, it's not officially on the roadmap, but that I think we would be keen to have as an input from the community and maybe some help. Out of time. A couple of links here, just from CoreOS installer to some Red Hat documentation on how we do simplified provisioning with FDO and Ignition. And that's it. All right, somebody any question? No? Probably not. Yeah, go, Chad.
Automotive, who will talk about quick booting a software-defined rear view camera. There will be a few minutes at the end of the session dedicated to our questions, and without any further ado, I'm giving the floor to the speaker.
Hi everyone. Is the mic working? That's only for the streamers, okay. Yeah, hi everyone. I already got introduced. It's my first time at DevConf. The venue is very nice, I must say, and thank you for attending the talk. I think it's about 28 slides, which is probably a lot, and I'm going to go through them rather quickly. But if there's anything that yeah.
I have trouble hearing.
I'll speak louder. The microphone is for the streamers on like YouTube. I'll speak louder. Thanks for letting me know.
If you got to your area, you said to the volume.
So yeah, I've 28 slides. I'm going to try and go through them rather quickly because I want to leave time for questions at the end. So if anything I said was really unclear or people were unsure about, feel free. I'm happy to take as many questions as possible. Okay, let me just get my pointer on this. Oh yeah, so I was already introduced. I'm Eric Curtin. I'm a software engineer at Red Hat. I work in the automotive org on all kinds of different things, I guess. So the scope of this talk, the scope of optimization can be quite large, but for this talk, we're going to focus on optimization techniques from Linux kernel and initRD boot onwards. So for example, what's something that isn't covered is anything before that, because firmware, etc., it's generally owned by the automotive board vendor. So the optimization of this area is out of the hands of an OS vendor, such as us. And obviously the firmware optimization is just as important. It's just something that's not my responsibility. So I do not go through optimization of the camera stack at the kernel level either, because we used a USB camera for this, and rather than an actual ISP SoC from a real automotive board. Although the same optimizations here would apply to an actual automotive board. Another thing I want to cover is there is a kind of a balance between keeping an OS generic and making it optimized to run some specific things early. So like you could trim down a kernel and user space to only display camera frames and do nothing else, but it wouldn't be a very useful automotive OS then. So yeah, I kind of split the talk in two. One is just generically starting an early boot systemd service, and then the second half I'll describe how we applied that to a camera application. And some of the techniques in this talk can be used to start other services early. In automotive in particular, there's an expectation to start all sorts of services kind of early. A rear view camera is just one of these. So here I did a little ASCII diagram of how kind of a Linux OS is booted from a certain perspective. So generally the firmware loads into some sort of bootloader, and normally that's where decompression of the kernel and init RAM disk occurs, even though that's not always the case, but normally. And then the first file system mounted is the init RAM FS, and that loads systemd and does a bunch of things. And then at some point we changed the root file system from the init RAM FS to the normal root file system. So you've two options at this point. If your systemd service, if it doesn't need to start super fast, like it needs to start after 3 or 4 or 5 seconds, maybe starting in the root FS is just fine. But if you want to start something super early, like in the case of a camera, you have to start it within the inner MFS, sometimes called init RD as well. They mean the same thing pretty much. So the reason why there's two options at this point is there's actually kind of a trade-off here. So when you start a service in the init RAMFS, if that requires you to add more binaries, libraries, etc. into the init RAMFS, it actually has a negative effect on the overall boot time because, but anyway, I'll go through that in a while. But we're going to use that technique for this talk because in the case of camera, you have to kind of start it super fast. These are some generic tips just to boot things quickly. They're probably obvious, but sometimes they aren't. So keep your kernel as small as possible and as modularized as possible. So anything that can be a kernel module probably should be. And keep the inner MFS small. But the kernel in inner MFS must be small, as I said earlier, because you actually pay a penalty for every single byte, because every single byte has to be decompressed before you can use it. So they're just generic tips. So if you want to start a service really early under a systemd based operating system like all the Red Hat operating systems, this is what it looks like. The one line that's probably important is that default dependencies equals no, because systemd services have a default set of dependencies, and the default for that is yes. And if you have that set as yes, your systemd service won't start until a couple of seconds because it must start all the default dependencies first. So in this case, we don't want that. This is just a directcut file used to pack things into an init RAM disk, and that's just, it just says put this file in this symlink in the init RAM disk. And if you do that and run a service like this, it'll actually start within about half a second. This is just how you rebuild an init RAMFS. So that technique is useful. Yeah, it's useful to know, because if you can, using systemd and using that technique I just described, you can start things within half a second. So if you need to start something within that time frame, that's a good technique to use. Now we're going to apply some of this to a camera application. So this has already been done in automotive in different ways, actually, but the existing approaches, they use firmware-based cameras and displays to launch and display a rear view camera, and this works perfectly fine. But it's difficult to maintain. It's hardware specific, and it's not software defined, so it can be difficult to develop for. And in fact, it's not even Linux, so it's just custom code. So this was my first technique I tried to start a camera quickly. It was something that exists already in Rails for Edge called kiosk mode, which is a mode to start a graphical application. And I won't play that video, but basically, if I played that, that was when I started. The camera would start after 14 seconds, which is clearly too slow. So we have to do something a bit more custom. So then I moved on to an optimized approach. So I was kind of discussing it with the team, and the first thing that came to mind is, what's the first graphic that Linux displays? And of course, it's the boot splash, which is Plymouth. Plymouth is the tool that launches the boot splash. So the technique I use for this, it takes a lot of influence from Plymouth, except the main difference is, in this case, not only are you just displaying graphical data, but you're also processing graphical input from a camera. I suppose that's kind of the key difference between this and Plymouth. So there's two main components to this. One is libdrm, which is part of Mesa, and the other one is libcamera, which powers the camera. Yeah, so I've gone through that already. So this is libcamera. The kernel guys that are involved with the kernel camera stack are pushing this library hard. It runs on Chrome OS and all the various Linux distributions. I think it even supports Android, but don't quote me on that. It's definitely running on Chrome OS and all the other distributions. It aims to be the Mesa of the camera stack. So if you're familiar with Mesa is basically the Linux user space graphics stack. So it supports various different types of cameras across multiple CPUs, SoCs, ISPs, etc. And it has decent support for things like DRM KMS, Pipewire QT, SDL, and yeah, it's basically the compatibility layer for all these things. So I wrote a little reference application where I tie all these things together to make it work. I called it TwinCam. So as I said, it's very similar to a boot splash, what we do here. It doesn't use a compositor or a window manager. Instead, we use the DRM KMS subsystem to write to the display buffers directly. And you definitely should not do this most of the time. Like, you should run your graphical application on top of Wayland and all of that. It's just for this use case, Wayland has so many dependencies, you could never start a graphical application under Wayland at the moment, at least, in around a second or two. It's just really hard. So in this case, there's a lot of custom code against DRM KMS to do it quickly. So yeah, Plymouth is another example of a tool that does things this way. But yeah, it's not recommended at all, unless you need performance and need to start something quickly. So this is how you normally install a camera application on a Linux system. So the init or the init ramfs normally initially loads all of these things, and the camera application is typically stored in the rootfs somewhere else. And that's what you should do if you don't have the requirement to start things really quickly. So to start the camera quickly, we basically moved anything that the camera requires into the init ramfs. And yeah, then we wrote a little systemd unit file that looks a little like this. It's very similar to the last example I showed you. I won't go through every single line, but another important line there is the ignore on isolate equals true. Because other systemd units can run in this isolate mode, but basically what that means is it can stop other systemd services, and we don't want that to happen. But yeah, not everything in this file is strictly required, but they're the important ones anyway. Those default dependencies equals no, and ignore and isolate equals true. And here is just the Dracode module.setup file to add things to the init ramfs. So the first function says make sure you have TwinCam in the init ramfs. This depends call, it just tells the init ramfs that we have a requirement on this graphics stack, so make sure that's there. Instamod's driver media, that's like that's the media subsystem in the Linux kernel. It's like where the camera kernel stuff is. So if you add that, you have kernel support in your init ramfs. And the final install is basically the TwinCam binary, libcamera libraries, libevent library, and the C++ library. I skipped a slide. So when you do all this, yeah, you can basically start the camera within 2 seconds rather than 14, which is the point where I started. So I'll I'll play a little demo of that I have recorded just to prove that I'm not talking nonsense. So what I tend to do is sorry, I have it on the wrong screen. Sorry, I had it on the wrong screen. So this is Grub Bootloader. I normally pause it at Grub Bootloader because this is an old, dusty Acer laptop I have at my house, and I'm not interested in optimizing Acer laptop firmware because it's for an automotive use case, not for a laptop. So I'll hit enter here on the keyboard, and you'll see the camera displayed really, really quickly. And there is me cycling a bike. So I think that's pretty much it. Yeah, so if you take the timings there, that starts at about 1.8 seconds from kernel boot. And actually, what's more important, because often in the automotive use case, sometimes the node processing camera frames is different to the display. So what's more important, if you actually check the timings, we start receiving camera frames at about 1.4 seconds, which is pretty decent. And this concludes the talk, but just some shameless self-promotion here. If you're interested in automotive or ARM enablement or any of this space, I'm doing another talk tomorrow on Fedora Asahi Remix, which is essentially Fedora and Apple Silicon. And the reason I'm involved in this is because ARM enablement, it's important for automotive because almost all automotive boards are ARM-based. So it provides me and many others in the community an affordable, well-upstreamed and powerful hardware to develop on and iterate quickly. So that's about it. Thanks very much. I'll take any questions if there are any. Yeah.
So if I understand it correctly, then even if the boot finish properly, we still continue showing the frames in the bootstrap mode and not flipping to Wayland or this or.
This is a good question that we have. Thanks. The question is, do I just keep on playing the frames indefinitely, or at some point do we like transition to Wayland? This is something we have to work out. It's a good question. I've spoke to we have an internal team that works on digital cockpit and that kind of thing. At some point, you should switch to Wayland and a long-term compositor. I just didn't cover that for the scope of this talk. But yeah, 100%, you don't want to be writing frames directly to the frame buffer like that in the long term. It's just to achieve the goal of initially seeing it really quickly, because that's a requirement. Yeah. Yeah, go for it.
You mentioned starting time for Intel machine. Did you also try with something with some ARM or something that more resembles ARM hardware, or do you expect the times to be comparable?
So the question is, did I only measure the times on an Intel laptop, or did I also run this on some ARM hardware that is more similar to what you see in automotive? So the answer is yes. At the start, all I had available to me was a Raspberry Pi. And yeah, the Raspberry Pi was much slower, as you'd expect. But there's a huge difference between a Raspberry Pi and an automotive board, because the Raspberry Pi costs €100, and an automotive board is like in the thousands. So going back to my last slide on the Apple Silicon thing, I've also ran this same thing using my Mac Mini, and I achieve roughly the same time. So it's roughly similar. And actually, most automotive boards, there isn't Apple Silicon running on any vehicles at the moment, at least. But an M1 is roughly similar in performance to what you would see in an actual automotive board. But I don't want to dismiss that point too much, because the hardware is important. Like, everything is important. Is the hardware fast? Is the storage fast? Is the camera stack fast? Everything matters. Is the firmware fast? Everything is important, of course, yeah.
You mentioned that you use compressed RDs.
Yeah.
Have you tried without compression, whether that makes a difference in the runtime or different compression algorithm?
I have. So the question is, I referenced the init.rd, which is compressed, and have I tried other techniques such as not compressing the init.rd, or maybe using a different compression algorithm? I did play around with that stuff, and I also tried not using an init RAM disk at all, which is another option. But it didn't make much of a difference, because I found the blocker was, for that laptop in particular, and other machines I tried, the blocker was generally the kernel spinning up its camera framework. That was normally the slowest part. When I tried those different techniques, I got pretty much the same time. So I didn't see the need to just change things for the sake of it. Like earlier on in the talk, I referenced you can actually start a systemd service as quickly as half a second, so it's not actually a huge issue. And another question at the back?
Have you looked at doing this with secure boot enabled and maybe Verity on the file system?
So the question is, have I also tried this with encryption turned on and things like DM Verity switched on? I haven't, but we have to look at that at some time. I will say on DM Verity in particular, I work on Red Hat's automotive operating system. For DM Verity in particular, I'm not actually sure we're going to actually use that for our verification. There's something called ComposeFS that Alexander Larson on our team is working on. And I think, don't quote me on this because it could be wrong, I think he's using FS Verity instead. But yeah, no, you definitely have to rerun things with encryption and all these chain of trust things turned on because it will have an impact, yeah. Arthur.
I really enjoy this talk, and it's nice engineering task to accomplish this. I really enjoy it. At the same time, I wonder, why I'm thinking about the car, you will have this implemented. I wonder why doing this way, and whether you consider, or the automotive industry consider starting the electronic unit in the rear view sooner in the moment I open the door, and silently start and then switch on the display when I pour on the car, which probably give me 5 or 10 seconds.
Yeah.
I have to change the fractions of the second.
Yes. Yeah, so the question for everyone online is, this is a really cool technique, but may the question is kind of like maybe we could cheat a little and start the boot when someone opens the door and this kind of thing, and you might not need this at all. And that's a very good point. Why this is still important is automotive companies definitely look into those things, like optimistically starting a car if you think somebody's going to start driving it soon. So to first answer the question, they look into that also. The second part of the question is, it's actually a certification requirement to start it really quickly from cold boot. So cheating only gets you so far. You mightn't pass all the certification requirements. And the third reason, if you just auto-start a graphical application like this out of the box, using Wayland and all this stuff, it's around 14, 15 seconds. So 14, 15 seconds is just way too slow. You definitely, you can do all the cheating you want in the world, but 15 seconds is way too slow. Question from... Absolutely. Actually, a follow-on to that point is what some automotive companies have looked into is just kind of resuming from suspend and a hibernate state, but that has a couple of issues. For example, if it's suspend and you leave it in a low power state, you're draining battery. But if it's more hibernate and you're loading from disk, there are still issues because would you feel safer in a car that clean booted from scratch or a car that woke up from a suspended state? A clean boot is arguably safer, but you could debate about those things all day. Yeah, I know, yeah. I'm not actually against that technique, but some people don't like it because it's not a clean boot, and they would say, is that system safe after suspending all that hardware and reactivating it? I don't know. I'm not very opinionated on that stuff. A question here.
Okay, maybe a remark, because if you start the engine, then there is a classical engine, diesel engine and so on, then there is high probability that the voltage goes low and maybe there is even the reboot caused by the power outage. So in such case you need to boot quickly or you need to reboot the system if there is a fire. So basically the preparation in advance doesn't help in such cases.
Yeah. That was a long question, but to repeat on the microphone, it was basically, do you need to start quickly in every case? My shorter answer is you kind of do, because it's actually a requirement for some certifications and such, and if you fail the test, you failed the test. So they will literally, a tester will come in and he'll step into the car, turn on the ignition, start a timer on his watch if he deems it to be sufficient pass or fail. Yeah. Any other questions? I'm just going to check the matrix really quickly, and if there's no questions there. Cool. Thanks very much, everyone. Thanks for attending. That's it.
I'm not going to be introduced, right? No, it's fine. Okay. Is there anybody who doesn't know me? Okay, so hello everybody. I'm going to be your last speaker today in this room about trust-based adaptive access control architecture. My name is David Hallis, and I work as a principal software engineer. Seriously, guys? So I work as a principal software engineer for Red Hat. I'm in my 9th year there. I also am a PhD student and researcher at the Masaryk University in Brno, Czech Republic, in the lab of software architectures and information systems. And I'm also an alumni of this school. You've probably seen those ducks outside on the corridor. This one with David text on it in the 2016 year is mine. My PhD research, which, come on,
Is your microphone on?
Yes, but it's not for you. It's for the recording. So my research at the university is about trust-based adaptive safety in autonomous ecosystems, which I'm going to talk about a little bit more. So what are software ecosystems? So if we combine multiple systems into one big unit, we can call them a systems of systems or ecosystems. It's some kind of evolution as we are creating more complex structures. And of course, such systems can provide much more than a single system. Ecosystems can provide more than a system. So if you think about an analogy from buildings, so an architecture of a regular house could be a software system, then the architecture of an ecosystem could be like a city with all these plans of every individual buildings inside. So this is what I'm researching. Like, this is the main focus. Of course, if we bring autonomy to the topic, so we don't talk about software ecosystems, but autonomous ecosystems or autonomous software or cyber physical ecosystems, we can get much more higher degree of autonomy as we have multiple actors in the world working together, collaborating or competing. Member systems can join or leave at any time, so context changes are producing a lot of unpredictable situations and a lot of uncertainty, which brings to the main topic of my research, is the safe and secure behavior of such systems. We're going to look into something that's really a really small focus field of this research, ecosystem coordination. By coordination, I mean, for example, if you have a set of cars in a multi-lane highway, you can coordinate them to move them in a single lane, reducing aerodynamic resistance, basically vehicle platooning. This can be called as an autonomous ecosystem of self-driving cars moving in one lane. So we can do ecosystems coordination in two different ways. One is sending messages, so we can ask these autonomous vehicles to talk to each other and have some implicitly implemented features that can react to these messages that they send. This is relatively safe because you have some pre-trained stuff that you already know it in advance, but it doesn't really give you flexibility of uncertain situations. Which we are looking into more is sharing software, so sending some kind of code, something executable between autonomous systems, which receivers can execute. Obviously, it's not that safe as sending messages because you can execute stuff, but it brings you the opportunity to have new features on the fly. For example, if you have these vehicles here, it's enough if one has the smart agent or the software module for platooning. It can share this software module with the other vehicles, which don't even support this feature, and after everything's working fine, they can move into one platoon, even though they didn't have this supported feature before. Of course, running a third-party software module on your autonomous vehicle in privileged mode is kind of a bad idea. I guess everybody can agree here that we shouldn't do that. But if it's a bad idea, it can be still fun. So our view of how to make it safe is to use the concept of trust. And by trust, I don't really mean the trust as you know in software engineering in general with trusted computing, trusted execution, or key pairs, encryption, and trust in HTTPS certificates. I mean more like trust as in human psychology or in philosophy, where you have some kind of relationship between a truster and a trustee, and the trustee is having some kind of vulnerabilities by trusting the truster. So we are trying to model something in this area. And somebody smarter than me said that reputation-based trust can be effective for securing communication, and our belief is that we can also use it for interactions, not just any kind of interaction, even physical interaction, not just communications. So our idea is to use trust as a decision factor in real-time evaluation. We already know that this trust will be not binary. So I'm not sure about the representation yet, but in a simple solution with binary, true, false, trust, not trust, you can have a lot of very, very dangerous false positive situations. So dual solution is definitely not something what we want. We are also looking into reputation, which is, we interpret reputation in a way that trust assessed by other actors, basically gossiping. So one, let's say autonomous vehicle has an interaction with another one, it has a bad experience and it shares with others. Basically the same as people gossip about other people, which is not nice, but in autonomous ecosystems it might be useful for us. So to calculate trust, if I say number, it might be a number, so we can go with that. So we would use this external reputation on these smart agents, software modules. We can use static analysis to find some kind of vulnerabilities there. The important part is, which is not my research, but I'm going to use it as an input, is predictive simulation using digital twins. And based on the result of these digital twins, we can do live compliance checking, which I will explain later. So, is anybody unfamiliar here with digital twins? Okay. So a digital twin in our case can model anything from the physical world. Basically, it's a digital representation of a physical object. In our case, the physical object can be the software module. Doesn't have to be, but I will explain why it was our solution. As you see it on the picture, what we do with predictive simulation is that in a simulated world, we run ahead of time and run some kind of simulations on the digital twin. And the smart agent, which is running in software, in case of software, the exact same stuff. In the real world, you can compare these two things, and based on that, you can assess some kind of trustworthiness, how much the model itself is trustworthy based on the predictive simulations, and also how the two differ from each other, which is the live compliance checking I was talking about. So I really don't know that how the trust would be. My best guess, and in our papers we talk about a percentage, but more and more research is pointing towards a vector of different aspects, so maybe like 5 or 6% based on some kind of metrics. But I'm pretty sure that we would like to go with this smart agent digital twin bundle with some digital signature because it gives us some extra safety. So if we talk about digital twins, this is our generic idea that we would verify the digital signature. If it fails, we don't care about the bundle. If it passes, we do static analysis. Again, if it fails, we don't care about the bundle. Then we verify the digital twin on some preset simulations. If it fails, we not just reject the bundle, but we also propagate the trust score to the world, telling others that this might be some untrustworthy software module or smart agent. Then we do some predictive simulations and execute it and do the live compliance check based on those results. This was a simplified thing, and I would like to show you the whole architecture, which looks like this, which is kind of complex, but we'll go into this more a little bit later. what it does actually, so it does predictive simulation of some scenarios using the digital twin. So you have some reality, and you can have some multiple scenarios in the future based on that reality, and you can do all the simulations with the digital twin. Compare the simulations with the results, that's the live compliance check. Based on that, we can calculate that trust score, in which case it can be a number, let's say 45%. And based on this score, we can set up a decision tree that would allow us to expose certain features to this smart agent, or on the other hand, conceal those features. Basically some kind of access control based on how much we can trust this module, based on reputation and other metrics. So again, looking at this, so we have some external reputation coming from other vehicles. We have the smart agent and digital twin coming to some kind of gatekeeper. We verify that digital twin on some preset simulations. Then we load it to the simulator. We load the smart agent to the sandbox. And these two entities work in tandem, calculate some kind of comparison that goes to the trust aggregator that creates a trust score. And based on the trust score, the sandbox basically has or not has access to certain features on the vehicle's platform. But, which might be interesting for you software engineers not really working with automotive and let's say different technologies in the cloud, if you squint on this a little bit more, what this architecture resembles you. You have some rules, you have some role, and based on the rules and the roles, you have some access. What if I say Kubernetes RBAC is something similar? And what if we could implement something trust-based in Kubernetes? So instead of RBAC, we could do something like TBAC, which would basically implement a similar architecture in the cloud. I mean, it would probably be totally useless in software environments, but I see it as a viable way of doing a proof of concept. And I heard some rumors that there is a team at Red Hat who tries to run containers on vehicles. Okay, somebody's shaking his head, so it might be not true. So it would be probably useless in a real cluster where you're running it in the cloud, some services, because you might not be able to run some kind of simulations. But in some edge computing cases, it might be useful. So that's our vision how and why we would like to run it in Kubernetes at some point. So to wrap it up, there is some future work that we are looking into. So based on this, we are trying to swap the smart agents with a pair of sensors. So we could calculate trust on sensors, and we can like trust or not trust the sensors, and based on that, believe or not what the sensors say. Another approach is to use digital twins of autonomous vehicles and extend this architecture for a whole ecosystem. So we could simulate other cars, calculate their trust score, and behave accordingly. So it wouldn't be just inside one vehicle, but the architecture would be extended among multiple ones. And the last one is that we just submitted a paper, and it's not yet accepted, is trustworthy execution in an untrustworthy way. So let's flip the concept that the smart agent wouldn't trust the execution environment where it's running. We had some initial discussions with people who understand blockchain, and this might be an unsolvable problem because the vehicle manufacturer might have some godlike power on your smart agent, but there are still ways how to detect that such thing can happen. So stay tuned for that. It might have some interesting results. And last but not least, I would like to mention that my supervisor will have a talk tomorrow at 5 o'clock. Or actually, I will do it because she twisted her ankle today. So if she recovers, then check out her talk. Otherwise, see me tomorrow as well. Thank you. Yeah, I try to make it fast because dinner.
Could you go back to the slide with validation?
Validation?
Yeah, a couple more, I guess.
Which one? This one?
This one.
Yeah.
Verification. Yeah. First I wonder why you don't notify the aggregator when the static analysis fails.
Sorry, I cannot hear you.
Why do you not notify the aggregator when the static analysis fails?
Because that would fail on any other vehicle. This is an architecture that has some kind of static analysis, so it doesn't really make sense because each of them would.
Okay. So they had different bundles, but the framework is always the same.
Yeah, well, the point is that everybody would implement this framework. They would have the same kind of static analysis, so they could catch the same issues. Anyway, the question was why the static analysis isn't notifying the aggregator.
When the aggregator is notified, what sort of safeguards are present in the aggregator against spamming of false positives or false negatives?
So the question is about how the aggregator gets protected from spamming, from false positives and false negatives. So the results are actually not coming from the smart agent, but the simulator that runs the smart agent. So the smart agent cannot really spam it.
It's the aggregator.
Yeah. Yeah. The aggregator gets a message from an existing component that's also under our control.
Okay, I thought it went back to
No.
bigger parts of the network.
Pierre?
Do you have any, I haven't seen that mentioned, but do you have any track record of editing of provenance? Do you keep track of the provenance? And that's where actually sharing the static analysis in the aggregator may be of interest, because you may build a repetition not only about the binary that is exchanged between vehicles, but where that binary originated from. And at some point, you may have a scoring mechanism that would impact how this binary originated from. And if your static code analysis always fails on binaries that is produced by that company, then the repetition of the next binary that's entering the system will be lowered anyway, because it has a track record of not passing static analysis. Which may lead to quicker decisions on how to or not to consider it, because all they have been sending so far is backwards.
Yeah, so the question was about track record and regarding the static analysis, that we might get some interesting reputation if from a certain vendor we have failing static analysis. We weren't really looking into specific vendors and track records, but this is an interesting aspect. Thank you. Yeah, go ahead. Just please be louder because I cannot hear from the AC.
A number of things that you've mentioned about the repetitions makes me think about the GPG signature process, where you sign a GPG and someone else signs the GPG that you have trust. There's a trust chain coding. So did you look into leveraging some of the ideas, or is there, outside of the concept of the trust chains that are built into OpenGPG and that you're replicating here, is there anything that you could leverage?
So the question was about GPG and trust chains, that the way that it resembles what we have with GPG and trust chain. No, we were actually trying to get around this topic of trust chain and static kind of trust. So our approach is trying to be dynamic, and we tried to avoid and throw away everything that was interpreted as trust in software engineering and computing. Any more questions? Please.
Okay, so since we are having there no more questions, so next week's conference, so
okay.
I think it's part of
Did you consider the weak element of this diagram, of this approach? What would be if you were to attack the system, where would you attack it? I can see two places where
Yeah, so the question was about vulnerabilities and attack surface, specifically in the trust aggregator and the trust gate. Well, the trust gate isn't really in that shape yet that I can talk more about the details, so it's just a high-level thing. Regarding the trust aggregator, there are already some research with some results on how to do countermeasures against such attacks. Mm-hmm. Yeah, so the trust aggregation and the calculation isn't really my research. My focus is more on this part on the left. Okay, I guess thank you for your attention.